Okay, assalamu alaikum. I decided to make this video, which is a big compilation of some videos that I've been recording over the last week. Basically, of me solving some exam questions, hopefully to help you study for the midterm exam, physics exam, that is. Now, I'm just going to talk about the physics exam briefly. So it's a little bit over 2 hours. It's made of three parts, and it's going to be the first part is going to be matching. So you're going to be matching some vocabulary. You're going to get some definitions. You're going to get some vocabulary, and you're going to try and match those. The second part is going to be multiple choice questions, and the third part is going to be problem solving. So this part here is going to be approximately 10 marks. The next part is approximately going to be 15 marks. Okay. And that third one is going to be 15 marks as well. And that's problem solving. And let's talk about those just in a little bit more detail. So part A, you're going to get to be familiar. You're going to get familiar with these vocabulary. You need to anyway. You're not always expected to. You're not going to be expected to actually write the definitions for these. But what you will be expected to do is actually recognize the definitions as you go along. So you'll have a list of definitions, and you're going to have to match that list with the definitions or the vocabulary that's given to you. Okay, so get familiar with these and any others that are in the book that are highlighted in bold. Okay, so that's the way I would do it. Is I would go through the vocabulary here and any others in the book that are highlighted in bold. Part B is simply the multiple choice questions, and that's so I'm going to show you an example of that in the video. And then part C is solving using the formula, workout, answer, units where possible. So what that means is basically if I say, for example, a car accelerates from 5 meters per second to 25 meters per second in the span of 5 seconds, work out the acceleration. You're going to tell me, well, acceleration is equal to change in velocity over time. And then you show me the workout. So it's going to be final velocity, which is going to be 25 minus initial velocity, which is 5, all over. I don't know if I can't remember if I said 5 seconds or 4 seconds or whatever. So that's going to be 4 meters per second squared. So over here, I've got the formula, I've got the workout, I've got the answer, and I've got the units. Okay. Now, as far as decimal places are concerned, try to stick to what the question shows you. So if the question has 2 decimal places, then try to stick to that. But we're not too concerned about it. So even if you go with 1 decimal place, that's fine as well. But what's really important though is make sure that you do the rounding correctly. So let's say, for example, the answer is 117.557. Now you're not allowed to say the answer is 117, but you are allowed to say the answer is 118 because the 5 rounds up. Okay. So the rounding is important. That is wrong. That is correct. You're also allowed to say it's 117.6. That's also allowed. 117.66 is also allowed. Okay, because that's the correct rounding. Okay, so that's all from me. Let's enjoy the video. Enjoy the revision, I should say. Best of luck for the physics. Don't worry about it. It's not too hard. You'll do just fine. Okay, all the best. Okay, assalamu alaikum. Welcome back. Today we are discussing the physics exam. You've got a midterm exam coming up, and this is what the purpose of the video is. It's going to be a revision for your midterm exam. So, needless to say, it is going to be slightly long as we will be solving all the questions in your midterm exam guide. Furthermore, what I'd like you to do is obviously, as I always say, please work through the problems as I go along. Make sure that you pause the video, solve the problem, and then check your answer with me once you've solved the problem yourself. Right, and with that out of the way, we might as well start talking about the exam. So the physics exam is obviously an important one. It's going to be made up of 40 marks. Okay, so 40 marks, and it's going to cover the following topics. It's going to cover experience one, which is displacement and velocity. It's going to cover acceleration, both 1 and 2D acceleration. It's going to cover circular and projectile motion. It's going to cover force, mass, and acceleration and how they're related to each other. Types of forces, which includes spring forces, as well as friction, tension, weight, and as well as forces on systems. So this is where we're talking about multiple objects that make up part of the system. So I don't want you to panic. Basically, this is what the whole point of the video is, to get you to relax. I have my tea with me. Make sure you've got your tea or coffee or whatever you need, and just sit there, relax, and let's work through them. You'll notice here that you have a formula sheet, so that's another thing that you need to get familiar with. In the exam, you will get this exact same formula sheet that you see in front of you now, and so it's quite useful to obviously get used to working with this one. So what I would do if I were you, if you don't have a copy of this, what I would do is I would print it out, okay? And as I'm doing my revision, I would be using this exact formula sheet, because then in the exam, I'm familiar with that same exact formula sheet. Right. And with that out of the way, we might as well make a start. Right. So the other thing as well in the exam is you'll need to answer in a specific format. So you'll notice that some of the questions are worth 2 marks, some of the questions are worth 3 or 4 marks. And what we're looking for is the formula, the workout, the answer, and finally the correct units. And you'll see how that works or how that looks once we start solving some problems. So make sure, please, that you have your calculator. Make sure that you solve through the same format, which is FWAU, which is formula, workout, answer, and units. And the reason why we do that is actually to benefit you. In case you make a mistake with the answer, with the final answer, we can still reward you some marks for the formula, the workout, and the units, right? In fact, you can still score most of the marks if you've got the correct workout. Right. Let's start with displacement and velocity. So here we've got a question that talks about a student who's walking from the library, which is x equals 0. So that's position 0. So that's it. That's the library over there. To the music room, which is at x equals 14. There's a music room. Passing through physics classroom, which is at x equals 5, right? And the maths classroom at x equals 8. So the person is moving, basically, just to put it simply, they are going from the library to the music room. What is the total distance traveled if the student walks from the library to the music classroom? Okay, so we need to work out the total distance. Now, first of all, you need to know the difference between distance and displacement. Distance is the total covered, the total length covered, whereas the displacement is the shortest length between 2 points, right? So we're asking for the total distance, which is the total length covered if they go from point 0 to point 14. So really, the answer is quite simple. It's going to be 14 meters, right? There's nothing to it. All you have to do is distance equals 14 minus 0, which equals 14 meters. Part B, okay, and that's Q1, obviously. Part B says, what is the student's displacement if they return to the maths classroom after reaching the music classroom? Okay, so now we need to think about this slightly harder. So they are going back to the maths classroom. So they've gone over here first and then over here. So they started here, that's the start, and they've ended here. Okay, that's the end. That's the start, and that's the end. So since we know the start and the end, we can work out the displacement, because remember, displacement is the shortest distance between 2 points. So it's going to be displacement, still haven't gotten used to writing on this piece of glass, is equal to 8 meters minus 0 meters. You don't have to put the units here. You just have to make sure that the units are there in the final answer. So it's going to be 8 meters forward. Okay, now why did I write forward, or why did I write to the right? You can also write 8 meters to the right, or you can even write plus 8 meters. Okay, you don't have to put the decimal point, you don't have to put the zero either. So all of these are correct. And why did we include the direction? Well, because we're talking about displacement, and displacement is a vector quantity. Okay, so since it's a vector quantity, you have to include the magnitude, which is the size, as well as the direction. Okay, so that's question one done. Let's go to question two. Question two says a hiker walks 4.2 kilometers to the north. Okay, so here's question two. A hiker walks 4.2 kilometers to the north and then goes down 1.5 kilometers, or kilometers if you prefer that. And so we're asked to work out, first of all, is the distance covered by the hiker greater than, less than, or equal to the displacement? Okay, so hopefully you should know that distance uh, can or displacement can never be greater than distance. So it's either going to equal the distance or it's going to be less, right? Because by definition, displacement is the shortest distance between 2 points. So if I show you an example, let's say, for example, I started at X and I ended at Y. I can go like that, okay, and get to Y. Now that's going to be a whole great distance, but the displacement is always going to be shorter. Of course, I'm representing displacement using a dotted line. Um, there is one situation where distance can be equal to displacement, and that's that the person walks in a straight line directly from point X to point Y. So you can see that distance can be equal to displacement, but it can never be less than displacement. Displacement will always be equal or less than distance. So is the distance covered by the hiker greater than, less than, or equal to the displacement? Well, let's see. The person had to start here. That's their start. And then they went all the way there. Okay, so that's point A, that's point B, and then that's point C. So that's what they did. So obviously they covered a whole great distance. And then for parts B and C, we asked to work out the distance and the displacement. So what I'm going to do is I'm actually going to work out the distance and the displacement and then answer part A. It's a bit of a bad question since you can't answer part A without answering parts B and C. So let's see, what is the distance? The distance is going to be distance, or D, okay, is going to equal 4.2 kilometers plus 1.5 kilometers, so to 5.7 kilometers. Part C talks about the displacement, and in this instance, the displacement is going to be delta D is equal to 4 plus 4.2 kilometers, because of course it's north, okay, so we need to have a direction, minus 1.5 kilometers, because that's going south now, so it's going to be 2.7 kilometers. And of course, if we put that 2.7 kilometers, or if you want to, you can say north. Okay, 2.7 kilometers north. Now, knowing that, let's go back to question or part A. Is the distance covered by the hiker greater than, less than, or equal to their displacement? Of course, the distance is greater, is greater, and the reason for that is because displacement, this is the explanation now, is by definition the shortest distance between 2 points. Okay, so that's how we answer that one. Okay, let's look at question 3 now. And question 3 says, um, while walking to class, you walk 25 meters down the hallway and then turn right. Okay, and then walk 15 meters down another hallway. What is the total distance covered? So what happened was you walk 25 meters down a hallway, and down here doesn't mean actually down, it just means you walking through a hallway. And then you turn right and you walk further 15 meters. So 15 meters this way and 25 meters this way. Um, what is the total distance covered? The total distance covered is going to simply be, so part A, I'm just going to change that to part A instead of 3, 1 to keep it consistent, is going to be 40 meters. So distance is equal to 25 plus 15, which equals 40 meters. What about displacement? Displacement is going to be, well, remember it's the shortest distance between 2 points. Now, if we start off here at A and we end up here at B, the shortest distance between 2 points is going to be this solid line over here. I don't know how to change the color in Word. Maybe I should learn how to do that, because that would make for some cool effects. Give me a second. Is that how it changed the color? Let's see. Oh, yay. That works very well. Okay, so R, resultant vector here, is going to be the displacement, because it's the shortest distance between 2 points. Now, in order to get that, we have to go back to the formula sheet and use this formula over here. A squared plus B squared equals C squared. Okay, Pythagoras theorem. So basically, D, or delta D, is going to equal, in this case, it's going to equal R, and we don't have to complicate things. We're just going to say the square root of A squared plus B squared, which is equal to the square root of 15 squared, which is 225, plus 25 squared, which is 525, I believe. So 15 squared plus 25 squared. Okay, and the square root of 850 is going to be approximately 29 meters. Now, why did I settle for 29 meters instead of 29.15, for example? Because obviously the calculator says 29.15 blah, blah, blah. Now, the reason for that is because if I look at the question, you will see that I've just sort of stuck with what the question says. In fact, I should say 25.2. The reason why I'm saying 25.2 will become clear in a minute. Because if you look at the question, it's to 3 significant figures or 1 decimal place. And over here, it's also to 3 significant figures and 1 decimal place. So it's just better to stick to the same thing the question tells you. If the question gives you 1 decimal place or 2 significant figures, then just stick to the same thing, right? Now, are we going to be that strict about it? No, but it's just good practice. Okay, so please get into the habit of writing the answer the way the question gives it to you. Right, let's move on. Okay, so that one's solved. Let's go to question 4. Okay, so question 4 says at a ski resort, a rope tow pulls you up a slope. Your displacement vector has a magnitude of 190. So this is going to be 190. Okay, from here to here, it's going to be 190 meters. And is directed at an angle of 26 degrees Celsius. Oh, sorry, not Celsius, 26 degrees, because we're not talking about temperature. Above the horizontal. How far have you traveled in the horizontal direction? Okay, so what they're looking for is the x component and the y component. Okay, so they're looking for both of these components. And in order to answer this question, you have to know your SOHCAHTOAs. Now, let's see if that's actually in the formula sheet. No, it's not on the formula sheet. Well, you need to be familiar with SOHCAHTOA for this part. So the way we do this is question 4.
And so basically what that means is sine theta, which is the angle, is equal to opposite over hypotenuse cos theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent. That's what SOHCAHTOA stands for. And so what are we trying to find? We have the hypotenuse. This is what this is. That's the hypotenuse. Oh, suddenly I don't know how to spell hypotenuse. Okay, hypotenuse. There you go. Now we're looking for the opposite. That's going to be part 2 here. So we're looking for the opposite, and also we're looking for the adjacent. And there are multiple ways of doing this. But let's just start by finding the horizontal distance, which is going to be the adjacent. So if I'm trying to find A, I can do ka, because cos 26 degrees is going to equal the opposite, or the adjacent, sorry, over the hypotenuse, which in this case is 190. And so therefore A is going to equal cos 26 times 190, which is going to equal 171 meters. Okay. Now for part B, we're looking to find the vertical distance, which is the opposite. So this time we're going to use sine or saw. So sine 26 is equal to opposite over hypotenuse. Therefore, it's going to be over 190 once again. So the opposite is going to equal to sine 26 multiplied by 190. So that's going to be 83 meters. So what we're saying here is that this is going to be 83 meters, while this is going to be 171 meters. Okay? All right, let's go to question 5. You row a boat across a river. As you can see over here, that's all question 5. You row a boat across a river that is 22 meters wide. While rowing, the river current moves your boat 35 meters down the stream. What are the components of the boat's resultant displacement? So that's going to be the resultant displacement, okay? That's the resultant displacement because it's the shortest distance between 2 points. And what is the magnitude of the resultant displacement? Okay, so the components of the resultant displacement, since we are talking about vectors here, part A, it's going to be this part here, which is 22, and it's going to be this part here, which is 35. So another way of putting it would be x equals 35 meters and y equals 22 meters. So those are the components. Whilst the next part, part B, what is the magnitude of the resultant displacement? Once again, we have to use Pythagoras theorem. So c squared equals a squared plus b squared. Let's just see how it's written here. A squared plus b squared equals c squared. So a squared plus b squared equals c squared. Therefore, c is going to equal the square root of 22 squared plus 35 squared. And of course, it doesn't matter if you put 35 first or 22 first. So 22 squared plus 35 squared, square root of that, and that equals 41. 41 meters. Since it's displacement, we usually include a direction, but it specifically asked for the magnitude. It didn't ask for the displacement, it asked for the magnitude of the displacement. So it just wants the size of it. So it's just 41 degrees, if you 41 meters. Now, if you're really pedantic, you can still say northeast if you want to, but you don't have to, okay? You can just say 41 meters. Right. Question 6. Your friend rows a canoe across a river 44 meters wide using GPS on her phone. She determined that her total displacement is 66 meters. If the current moves her canoe downstream and her rowing speed is 1.5 meters per second, calculate how far down the river the current moved her canoe and the time it took for her to cross the river. So this is a nice question because it kind of involves um, speed and velocity and all of that stuff as well. So the first thing we need to do is find out the x component, if you can call it that. So we've got the same situation as this, and what we have is the river is 44 meters wide, so we've got 44 on this side, and we've got the displacement this time, which is 66. So we're trying to work out this guy here, okay? So we got to work backwards basically. So it's going to be a squared plus b squared. So that's a, that's b, and that's c, yeah? So a squared plus b squared equals c squared. So if we're trying to find b, then b squared is going to be c squared minus a squared. And then b is going to be the square root of c squared minus a squared, right? So it's going to be the square root of 66 squared minus 44 squared. And then the square root of that. So b is equal to, b is equal to 49. B is equal to 49 meters. That's part A. Now part B is asking us to the time it took for her to cross the river. Now we know that speed equals distance over time, right? And so, or if you prefer, we can write it this way: speed, distance, time. Now it's asking for the time. We have the speed. The speed says 1.5, so 1.5 meters per second is equal to the distance it took her, which is, okay, so the distance here is going to be right, I see. So which distance do we use? Do we use the C, or do we use A? And the way we solve this is by thinking about velocity. We have the velocity that's her rowing speed downstream. Okay. If the current moves her canoe downstream and her current rowing. So we know that her velocity this way is 1.5 meters per second, but we don't know her velocity in this direction. We don't know what the actual speed of the river is, and we certainly don't know her speed across the resultant vector. So since we don't know that, we got to use this. We got to use that, okay? So obviously using the correct width of the river. So the width of the river is 44. So it's going to be 1.5 equals 44 divided by time. And therefore, we're going to use time is equal to 44 divided by 1.5. So it's going to take it 29 seconds. So 29 seconds to cross the river. Okay. And that's those sorted. Let's keep going. Question 7. The position versus time graphs A to E shown represent the motion of the objects. Which graphs show an object moving with constant velocity? Explain your answer. Now, constant velocity, remember this is position time. So the gradient of a position time graph is going to show the velocity, right? So this is going to be constant because the gradient is constant. As you can see here, if I measure the gradient, the rise over the run between those 2 points, the beginning and the end, this point here and this point here, we can see they're the same. The gradient over here is the same. So which graphs show an object moving with constant velocity? It's going to be both A and C. They're both moving with constant velocity. Um, because the gradient doesn't change. The gradient represents the velocity. So my explanation to that would be the gradient represents the velocity, or the slope represents the velocity, and the velocity doesn't change from the beginning to the end. If you measure the rise and the run for both the beginning and the end of each graph, so this point here, for example, and this point, and then this point here and this point, you'll see that the gradient or the slope is exactly the same. Right, so that's A. Part B says, which graphs represent an object at rest? Well, at rest means it's not moving at all, so the position is not changing. And the only one that I can see where the position is not changing at all with time is going to be B. So that's B. And finally, C says, which graphs show an object experiencing acceleration? Well, acceleration means the gradient is going to change, because remember, the gradient or the slope represents acceleration. Now, if I look at what I'm going to do is I'm going to zoom in. If I look at this here, the gradient is the tangent. And so it's like that at the beginning. And then over here, it's like that. Okay, so obviously it's increasing. And over here, it's like that. And then over here, it's like that. So this one is decreasing. So this one is decreasing while that one's increasing. Right. So what does that mean? Um, which one is experiencing acceleration? Well, in this instance, we can say that graphs D and E both show acceleration, because acceleration is the change in speed. Now, some of you might be confused, like, oh, isn't deceleration, that's deceleration? Well, deceleration is a form of acceleration. Acceleration is either speeding up, slowing down, or changing directions, right? So all of these fall under the umbrella of acceleration. Acceleration means all three things, either speeding up, slowing down, or changing directions. So since this one is speeding up, um, okay, then that's acceleration. And since this one is slowing down, that's also acceleration. So the answer to this is going to be both D and E. Now, had the question said which one is decelerating, then it would be E. But since it just said acceleration, you got to include both D and E. Now, some of you might just say, well, it's E, but it's also, sorry, D, but it's also E as well. Right. Question 8. Describe the motion of the object. So we've got an object that's moving A, B, C, and D. Describe the motion of the object in segments A, B, C, and D. Okay, well, this is hopefully should be should be quite easy as well. We should know by now what this is: a position time graph. So since it's a position time graph, the slope represents the velocity. Okay, so the first part A, it is moving forward with positive acceleration. So it's moving forward with positive velocity. Did I say acceleration? I'm sorry, there's no acceleration. There's no acceleration because the slope doesn't change. The gradient is the same. So it's moving forward with positive velocity. Part B is stationary. Stationary at 15 meters. So it's not moving, it just stopped for about 5 seconds. Part C is moving backwards. Moving backwards, and I would say, so that's negative velocity. Okay. And so that's from 10 to 15. And part D is moving forwards once again. Moving forwards. And once again, that's positive velocity, but a lot faster, than before. So it's positive velocity, and it's much faster than before as the gradient is steeper. So we can tell that it's actually faster. Okay. Um, right. So that's part A. Part B. Calculate the velocity of the object during segment A, given that the position changes from, okay, in 5 seconds. So they want us to calculate the velocity in segment A, and we should already know, hopefully, that the velocity is going to be equal to the slope. So it's going to be rise over run. So velocity is equal to rise over run, or if you prefer, change in position over time, uh, which is what we have here, distance over time. So it's going to be 15 meters divided by 5, which equals 15 meters divided by 5 seconds, which equals 3 meters per second. Okay. And part C, during segment C, the position decreases from 15 meters to 0 meters in 5 seconds. What is the velocity of the object during this segment, and is it positive or negative? So during part C, it's going to be 15 minus 10. The velocity is going to be, well, actually, the final position minus the initial position. So it's going to be 5 minus 15 all over the time, which is 5 seconds, because that's 15 minus 10. So it's going to be negative 10 over 5, or negative 2 meters per second. And it's negative because it's going backwards, essentially. Okay. All right. So I think we'll stop there for now, take a break, and I'll see you in a second. Okay, and hello again. You probably didn't even notice I took a break, but we're back. Right, let's go to question 9. Calculate the acceleration of the object during segments A to B. Okay, so what they're asking for is obviously the gradient. So what we need to do here is calculate the slope or the gradient, because the slope of a speed time graph or a velocity time graph is equal to the acceleration. So in this case, it's going to be acceleration equals change in velocity over time, which basically just means final velocity minus initial velocity over time. So since we're looking at section A, you'll notice that the final velocity is over here, 15, and the initial velocity is over here at 0. So it's going to be 15 minus 0 all over the time, which is 10 seconds, because we're only interested in this segment over here, and this segment is 10 seconds. And so it will be, 1.5 meters per second squared. Okay. Number 2 says, this is all question 9, obviously. Number 2, during segment D to F, so that's this one here. Okay. What about it? The speed decreases from 25 to 0 over the course of 20 seconds. What is the acceleration, and is it positive or negative? So the acceleration is going to be, once again, change in velocity. The final velocity in this case is 0 minus 25 all over 20 seconds. So it's going to equal, well, 0 meters per second minus 25 meters per second all over 20 seconds. So it's going to equal 1.25, negative 1.25 meters per second squared. Is it positive or negative? It's negative, obviously. It's decreasing because it's going from high to low. Right. What is the total time during which, so this is now number 3, what is the total time during which the object maintains a constant speed? Okay, so the constant speed, here's the speed over here. Constant speed, there's only one situation where constant speed is happening, and it's B to C. Now they're asking about the time during which the object maintains constant speed. So the time is between 10 seconds and 20 seconds. So a duration of 10 seconds. A total time of 10 seconds between 10 and 20 seconds. Okay? Calculate the total distance traveled by the object during segment B to D. Okay, so we're looking at the area under the graph because the area under the graph represents the distance, right? So we're looking for this. So what I'm going to do is I'm going to cut this area into two sides. I'm going to call this A, and I'm going to call this B. And so A can be calculated by just going height times width. So area of A equals 15 times 10, which is 150 meters. It'll be 150 meters because we're multiplying speed by time, and so the seconds cancel out. And area of B equals, we've got 150 plus, see, we've got 150 same as A, plus we've got this triangle over here. So this triangle is going to be half base times height, because that's the area of a triangle, which is going to be, the base is 10, from 20 to 30 is 10. So the base is 10, half of 10 is 5, multiplied by a height of 10 is equal to, let me just get rid of everything here because now it's getting a bit messy. So we've got three areas. We've worked out this is 150, this is 150, and now we're trying to work out what this is, which is going to be 5 times 10, which is 50. Okay, so it's an area of a triangle. So what you can do is like work it out like a square or a rectangle and divide it by half, which is what I normally do. Or you can go half base times height. Anyway, it's 50. And so the total area is going to be the total distance. So total distance is going to be total distance from B to D equals 350 meters. Okay? And that's how to do that one. Let's just check that everything is okay. Travel during segments B to D. Yes, it's 15 times 10 times 2 plus, that's going to be 5 times 10. Yeah, that's okay. Right. Let's go to question 10. And question 10, I can do better than that. Once again, it's about a graph. The graph shows the velocity of an object over time. What is the acceleration of the object during the interval from 20 to 30 seconds? Is it positive or negative? So by now we should know how to do these. They're just the same. From 20 to 30, obviously it's negative, but this time it's velocity time. From 20 to 30, it's negative. And I can tell you exactly what's going to be. Acceleration is equal to change in velocity over time, which is going to be final velocity, which is 0 minus initial velocity of 12, all over 10 seconds. So it's going to be negative 1.2 meters per second squared. Don't forget that the unit for acceleration is meters per second squared. And once again, we've got the formula, we've got the workout, we've got the answer, and we've got the units. So you need all of those four things, 1, 2, 3, 4, to get the 2 marks. Otherwise, you'll get 1.5 marks if you miss out on the units, for example. Um, okay, question 2. Calculate the total distance traveled by the object during the first 20 seconds. So once again, they're just asking for this area, which is going to be 12 times 20. So total distance is going to be, if you prefer to do that, if you're a calculus whiz, is going to be base times height. So there's the formula, which equals 20 seconds multiplied by 12 meters per second. Now, of course, time times speed equals distance, because speed equals distance over time. So if we want the distance, we multiply the speed by the time. And so this is the speed, this is the time. And so we have velocity is speed with direction, in case somebody's having uh, any thoughts about that. So 240 meters. Okay? And that's what that is. Okay. Calculate the distance for the first 20 seconds. We did that. What is the total distance traveled by the object during the entire 30 seconds? So we know it's going to be 240 plus half base times height, which is this one here. So area B. So it's going to be area B is equivalent to 10. Now, some students will make the mistake of going 25 times whatever. No, it's half the base, and the base is only 10. So it's 10 to 30. So you need, like, the length of the base is only 10, right? Okay, so that's 10, and that's 12. So it's going to be half times 10 multiplied by 12. So it's 5 times 12, which is 60. So it's going to be a total of 300 meters. Okay. All right. Yeah. Okay, let's move on. Question 11. A boat moves slowly inside a marina with a constant speed of 1.5 meters per second. As soon as it leaves the marina, it throttles up and moves with a constant acceleration of 2.4 meters per second squared. What is the velocity of the boat after accelerating for 5 seconds? Okay, so this is where we get into the kinematic equations. So what is the velocity of the boat after 5 seconds? So what do we have? Remember, the way we do these is, first of all, we look at what we have. Move slowly inside the marina with a constant speed of 1.5 meters per second. As soon as it leaves it, it throttles up. So we have VI, which equals 1.5 meters per second. We know that's VI because the question tells us it started off at that and then it accelerated. And we have the acceleration, which is 2.4 meters per second squared. Okay. And we have the time, which is 5 seconds, right? Time equals 5 seconds. So what we can do here is work out the final velocity of the boat, which is VF. And how do we do that? Well, we can use, if we go back to our formulas, our formula sheet, we can use VF equals VI plus AT, right? Here we go. VF equals VI plus AT. And so, so much easier if you know the formulas, by the way, but I know it's a bit tricky for some students to learn those. But try and learn them. It's so much easier. VF equals VI plus AT. And that is the worst plus I've ever drawn. Here we go. Which is equal to 1.5 plus 2.4 times 5. 2.4 times 5 plus 1.5, so that's going to be 13.5 meters per second. That is the final velocity. And if you wish, you can say positive if you really want to put a direction in there. Since it is positive, you can just say plus. So that indicates the fact that it's got a direction, it's positive. Okay, let's look at question 2 of that question, part 2 of that question, I should say. How far does the boat travel? Oh, excuse me. How far does the boat travel during the 5 seconds of acceleration? Okay, so now we're going to use a different formula. And if you remember from our kinematic formula days, we can use this formula here. Excuse me, plus. Oh, this is terrible. How come I can't draw pluses today? Half at squared. Now, the reason why we're using this is because we literally have everything we need. So they're looking for the distance, right? Because it says how far. How far means distance. And so that's going to equal 1.5 multiplied by 5 plus half times 2.4 times 5 squared. A grand total of 25 times 2.4 times 0.5 plus 1.5 plus 7.5, and that equals 37.5 meters. That's the answer. Okay, so that's that one done. Wasn't too hard, was it? No, look, it's just about taking your time, read the question. The first thing is make sure you know what the question is asking. If it's asking how far, that means we're looking for distance. If it's asking how long, it means it's looking for time. So please make sure you read the question carefully so you can answer the question. Basically, if you don't know what the question is asking, you won't be able to answer it. So make sure you read the question twice and answer once, and don't try and talk yourself out of an answer. Just answer once, go to the next question, and right at the end, revise and then look into it one more time. But yeah, just answer once. Okay, let's go to question 12. A drag racer starts from rest. Okay, and accelerates at 7.4 meters per second squared. How far? So that means distance. Will the racer travel in 1, 2, and 3 seconds? So we're using the same formula, essentially. We've got everything we need. So what I'm going to do in this case is I'm just going to draw like a table. And I'll write the formula once, because remember that's part of how we answer questions in the exam. And then for the workout, I'll put the workout in these rows. So it's going to be, for the first one, here's delta D. It's going to be 0 times 1, so we can ignore that altogether. So it's going to be half times 7.4 times 1 squared. Next one's going to be half times 7.4 times 2 squared. Third one's going to be half times 7.4 times 3 squared. And so we should get 3.7 times 1. The next one is going to be 3.7 times 4, 14.8. And the third one is going to be 3.7 times 9, 33.3 meters. Okay? And I've decided to stick to 3 significant figures. So that first one should be 3.70. But once again, we're not really that strict about that. I just want you to get the right answer. That's what I'm more interested in. Try and stick to what the question's asking, what the question's doing. So three significant figures, two decimal places, then try and keep that consistent with your answer. Right. Question 13. And question 13 is asking about, um, once again, it's the same thing, kinematic equation. So at t equals 0, a bunny is hopping along at a constant speed of 2 meters per second. I love bunnies, by the way. I'll draw one just for the sake of it. Here you go. That's my picture of a bunny. All right. A bunny is hopping along at constant speed of vi equals 2.0 meters per second and continues speed until time 20 seconds. So it seems like the t is going to be 20 seconds. When it begins to slow down with a constant acceleration coming to a stop at t equals 25. Okay. 25 seconds, and the final velocity is 0. But that's only between t and t2. So what's happening is this, right? So if I have velocity and I have time, so up until 20 seconds, it's traveling at 2 meters per second, and then it comes to a halt after the last 5 seconds. Oops. It goes down like this. This is what the graph looks like. What is the bunny's displacement during the first 20 seconds? Well, I can once again use the formula, but I don't need to. I mean, if you prefer to use the formula, you can go, well, delta d equals vit plus half at squared, and then there's no acceleration whatsoever, so it's going to be delta d is equal to the initial velocity times the time, which is 20 seconds, so it's going to be 40. But really, you can see, like, from the graph, it's pretty obvious. It's going to be 2 times 20, which is 40. So that's one way of working it out. In this case, if you do use a graph, then that would be in place of your formula, right? It'll be like showing the workout, and then you'd say, well, the area, I'm trying to work out the area, which is base times height. So you'd be like area equals base times height, or displacement is going to equal velocity times time, or whatever. Right, so that's 1, 2. What is the bunny's displacement while slowing down from 20 to 25? Well, once again, you can do it both ways. So you can use the half base times height, which would be 2.5 times 2, which is 5. So there's the displacement. We've already worked it out. But if you want to do it a different way, you can do it using by working out the acceleration, right? So first, the acceleration at the last bit is going to be change velocity over time, which is going to be 2 minus 0. Oh, sorry, 0 minus 2, because that's the initial velocity. That's vi, which is 2, and that's vf, which is 0. So it's going to be 0 minus 2 all over 5, and that's going to give me negative. Did I do something wrong before? Just checking. Yeah, so negative 2 divided by 5. So that's negative 0.4 meters per second squared. And so now, using the formula, I will know that delta d is equal to, I just need the last bit. So I don't need to work it out from the start. VIT. So it's going to be 2 times 5 plus half times negative 0.4 times 5 squared. Now, I wouldn't recommend you do it this way, but if that's what you want to do, if that's what you're comfortable with, because I know some students are just way more comfortable just doing it using the formula. And then so, yeah, that gives us 5 meters, which is what we got before. So multiple ways of doing things. Okay? Okay, let's keep going. Let's try and get to, yeah, the fun stuff. Okay. Your friend throws a rock off a cliff straight down with an initial speed of vi equals 10 meters per second. Using a stopwatch, you determine that it takes 3.2 seconds for the rock to hit the ground. What is the rock's velocity just before it hits the ground? So that means they want final velocity. So what do we have? Once again, what we have is vi equals 10.0 meters per second. We have t, which is 3.2 seconds. Now, some of you might be wondering, well, hang on, we need three things. Well, don't forget the g, which is acceleration towards gravity. And if you prefer, you can do that. And that equals 9.8 meters per second squared down. Or if you want to, you can write negative 9.8 meters per second squared. What is the rock's velocity just before it hits the ground? Well, we can use the kinematic equations. We have at and vi, which is the initial velocity. So if we go back up, we've got a. We want vf, don't we? We've got t and we've got vi. So we can use that one. Vf equals vi plus at. Yeah? And so, since we're using that one, let's write the formula first, because we got to try it the proper way. Formula, workout, answer, units. Vf equals vi plus at, which means 10 plus 3.2 times, oops, let me just do it in the right order, otherwise I'll have some students complaining. 9.8 times 3.2 seconds. Now here's the thing, just gotta be careful. Yes, the acceleration is negative because it's going down, but don't forget that the initial velocity is also negative because it's also going down because it's being dropped. So yeah, it's not being dropped up, or it throws a rock straight down, so it's also negative. So if you're going to make that negative, just make sure that you make everything else the right what's the word I'm looking for, the right sign, okay, the right direction, I guess. So here we go. So negative 10 because it's going down, plus acceleration is going down times this, so it's going to equal negative 9.81. Well, you can use negative 9.81 instead of negative 9.8, by the way. Negative 9.81 times 3.2 and minus 10. So it's going to be negative 41.4 meters per second. Not squared, sorry, meters per second only, because it's velocity. So VF. Now we don't need to say down because it already has the negative in it. So that's like a direction thing anyway. Okay. Let's do question 15. Running out of space a bit. A ball is thrown upwards. Okay, so now it's thrown upwards and reaches a height of 100 meters. Before coming down to its starting point, what is the net displacement of the ball? Okay, so displacement is going to be final velocity minus initial velocity. Excuse me, I need to take this phone call. I'll get back to you. Okay, and so, sorry about that. I just had to take a phone call. Where were we? Displacement. Yeah, so displacement is going to be final xf minus xi, which just happens to be back where we started. So this is xi. It goes up and it comes down. And this is xf. It's the same actually. Sorry, this is a bit confusing. Um, Here's XF, XI, and XF. They're the same point. Okay, so you throw it up and it comes back the same point. And so it's zero. Obviously, the displacement is going to be zero because displacement is the shortest distance between 2 points, shortest distance between 2 points, and it came back to where it started, therefore zero. Let's look at part two. What is the net distance? The distance is going to be 100 meters up, 100 meters down, so it's going to be 200. So work out, right? Distance equal 100 plus 100, which is equal to 200 meters. Now, some of you might be going, there's no formula there. It's not always going to have a formula. It's fine. Okay. I mean, I could write a distance formula just for the sake of it. I mean, I could say speed times time, which doesn't make sense in here. I could say total distance is equal to d1 plus d2. You don't have to do that. Okay, you can just, it's fine. Okay, since it's only 2 marks, just write the workout and the answer and the units. You're fine. Okay, question 16. A car starts from rest and acquires a velocity of Vf equals 54 kilometers per hour in 2 seconds. What is the acceleration of the car? And what is the distance traveled by the car? Assume the motion of the car is uniform. Okay, great. I will pause the video for a bit. I'll let you answer this one. I'm going to take a quick break. I'll be back in, well, as far as you're concerned, I'll be back in half a second. Okay, and we're back. I just realized I never answered part 2 of question 14. So that's part 1, and that's 41. No. Oops. Yeah, that's better. 41.4. So part 2 of question 14 is asking for how high is the cliff, right? So once again, we have to use this formula. Delta D is equal to VIT plus half AT squared. Which is going to equal 10 times 3.2 plus half times 9.81 times 3.2 squared. Negative 10 times 3.2. Now, of course, I'm going with negative 10 because the initial velocity is going down since I'm using acceleration as negative 9.81. 0.5 times negative 9.81 times 3.2 squared. Excuse me, I've got the flu. Okay, and that gives me a result that's quite interesting. It gives me a result that is negative as well. Am I surprised though? Negative 82.2 meters. No, I'm not surprised. The reason why it gave me a negative result is because it's displacement, and displacement is able to be negative. So that's the cliff. The rock was thrown over the cliff, so it's negative 82.2. Okay, sorry about that. I didn't even realize I didn't answer that one. Okay, question 16. A car starts from rest and acquires a velocity of 54 kilometers per hour in 2 seconds. Now, that's a very fast car, by the way. What is the acceleration of the car? Okay, so the first thing we need to do is realize that that's in kilometers per hour, and the time is in meters per second. So I need to figure out what 54 kilometers per hour is in seconds, in meters per second. So the first thing to do is convert 54 kilometers per hour to meters per second. And that's going to be 54,000 meters, because 54 kilometers, the word kilo, just means 1,000. So 54,000 meters divided by 60, that gives me 900 meters per minute. And if I divide by 60 again, gives me 15 meters per second. So once I know how much it is, or yeah, so it's 15 meters per second, or how many meters per second, I can work out the acceleration, because now we still haven't figured out the acceleration. Acceleration equals change in velocity over time, which equals 15 minus 0. Why 0? Ooh, remember that word. Starts from breast. Over time, which is 2 seconds, and that equals 7.5 meters per second. 7.5 meters per second squared. Okay, and question 2 is asking for what is the distance traveled by the car? Assume the motion is uniform. Once again, so I assume it means in those 2 seconds. So delta D is going to equal VIT, which we don't need because VI is equal to 0, plus half AT squared. So it's going to be half times, don't forget that the acceleration is not 9.81, it's not falling. It's it's in a horizontal direction. It's 7.5, because that's where we worked out before, times 2 squared. So it's about 15.5 times 7.5 times 4, and that is 15 meters. Okay, so we've solved that, and that completely. What did I do? What did I do? Here we go. Let's go to question 17 now. Question 17, an airplane. An airplane with a velocity of 150 kilometers per hour due north. A wind blows west at 30 kilometers per hour. Draw the resultant velocity vector of the airplane. Okay, that's really cool. So obviously head to tail. So that's the first one, 150. And that's the second one. And that's going to be 30. And the resultant is this guy here. And that's the resultant vector. Okay, calculate the magnitude of the resultant vector relative to the ground. So obviously that's 1. The magnitude is going to equal a squared plus b squared equals c squared. So c is going to equal the square root of 30 squared, which is 900, plus 150 squared, which is a big number. It's like 22,500 or something. 150 squared is 22,500 plus 900. So it's going to be the square root of 23,400, which equals 153 kilometers. Remember, we're working with kilometers. We haven't converted to meters, but we don't have to because the question didn't say we should. Okay, per hour. Oh, is that the full answer? No, we should say one more thing, northeast, because it needs direction. Okay, and number 3, determine the angle of the resultant velocity relative to the north direction. Okay, so relative to the north direction, we want the angle, so that's going to be that. And so it will be, that's the opposite, that's the adjacent. Tan would be the one to go for here. Tan theta equals 30 over 150. So it's shift tan 0.2. 30 divided by 150, shift tan the answer. And so the angle is equal to 11.3 degrees northeast. Okay. All right. I think I'll stop there and I'll see you in the next one. Maybe I'll be wearing the same clothes. Maybe I'll wear different clothes. Depends on whether I'm going to continue doing this today or I'm going to be doing it some other day. Okay. Catch you soon.
Okay, welcome back. Let's continue. We have question 18 to get through. Let's see. So a child walks at 0.9 meters per second in the direction opposite to the moving sidewalk, which is just a conveyor belt, the same ones you see at the airport, which is moving at 0.6 meters per second. What is the child's resultant velocity relative to the ground? Okay, so we have a child who's, this is question 18. So we have a child that's walking at a velocity of 0.9 meters per second in the positive direction, although it doesn't say whether they're moving to the right or the left. So I'm just going to put an arbitrary direction over here. And then they are walking on a conveyor belt, which is moving at 0.6 meters per second in the opposite direction. So therefore, their velocity, their resultant velocity is going to be 0.9 meters per second minus 0.6 meters per second. And the reason why it's minus because it's moving in the opposite direction, and obviously it's going to be 0.3 meters per second. The only thing I'm going to add is I'm going to make it positive, and that way, because I don't know the direction, making it positive makes it, it just means that it's going forward. So the person is going forward at 0.3 meters per second because that's what they started with. The child is walking at 0.9 meters per second in a direction opposite to the moving sidewalk. So we don't know what the direction is, whether it's the right, left, north, south, or whatever. But this way we can just say they're moving in the same direction they were going. They were just going at 0.3 meters per second positively. Okay, so the positive becomes the direction in a way. Let's do question 19. Ahmed throws a ball of a 50-meter cliff with a horizontal velocity of 3 meters per second. How long will it take the ball to strike the ground, and how far horizontally will the ball travel before hitting the ground? Okay, very nice question. So please pay attention to the steps. Basically, what we have here is we have a cliff. The cliff is, excuse me, just so you know, I'm recording this a few days after I've recorded the first part, the first and the second parts, because this is the third part. And I've been sick for a while, so excuse my voice. Hopefully, it'll get better as I go along. Okay, 50 meters here, and the horizontal velocity is going to be 3 meters per second. How long will it take to strike the ground? So the first thing I need to find out is there is an object being thrown here, and it's going to strike the ground, and it's going to take a certain time to strike the ground. So how long will this time be? And the other question is, how far horizontally will the ball travel before hitting the ground? So I need to know what this distance is going to be as well. Okay. So the first thing we need to realize is in order to find the time, we look at the y, okay? So I don't know if you remember this from when we used to do this, but in order to find the time, now in case you're wondering, I know time is not spelt this way, but I always spell it this way when I'm doing this, because that way you remember that in order to find the time, you use y. There are two components here. There's the x component and the y component. And so we are going to use the y component. What is the velocity in the y? What is the initial velocity in the y? So the initial velocity in the y direction is going to be VIY, and that equals 0. So as the ball is being pushed to the side, but it's not being pushed down. So therefore, the initial velocity in the y is 0. So we have that and that equals 0. What else do we have? We have the displacement slash distance, because they both agree in this instance, as it's a straight line down. So we have that, which is 50. Now, if you want to be pedantic, you can say it's minus 50. Now, why is it minus 50? Because we started on top and we went down 50. So if you wanted to, you could say it's minus 50 meters, but it really doesn't matter, okay? You can just keep it at 50. And then we've got the acceleration towards gravity, which is negative 9.81. Now here's the thing, because I said negative 50 here, I'm going to say negative 9.81 meters per second squared here. Otherwise, if I don't say the negative here, then I don't have to say the negative here. But if I said the negative here, then I'm going to say the negative here. Direction matters, especially when you're going to use it across the board for everything in the formula. So the formula we're going with is we're trying to find the time. So we're going to use this formula here. Delta D equals VIT plus half AT squared, right? And so if I use negative here, then I have to use the negative here, because the direction, if the direction of the displacement is downwards, then I have to acknowledge that the direction of the acceleration is downwards. And this is a question that many of my students ask me, like, is acceleration going to be negative? Fine. You know what? You want to make it negative? Fine. You can put negative 9.81 as long as you acknowledge that the displacement is also negative. So then it works. But if you don't make it negative, then you don't have to make the other thing negative either. So if I say this is 50 and VI is 0, so the whole thing is moot, which means it's unnecessary because 0 times t equals 0, since VI is 0, and then plus half times 9.81 times t squared. Right, now you see, now it's going to work properly because I just got rid of the negatives anyway. So I got rid of the negative from one side and the other side. But you can put them in, it doesn't make a difference. The answer is going to be exactly the same. And so therefore, if I do some mathematical gymnastics, I can say that 50 divided by half times 9.81 is equal to t squared. And therefore, this means therefore, because I've been asked about the three dots as well, therefore t is equivalent to the square root of 50 over 5, which is approximately 10, and so the square root of 10 is going to be approximately 3.1 or 3.2, somewhere around there. 4.9. Let me just work it out. So 50 divided by 0.5 times 9.81. So that's 3.2 seconds. Now, the other thing I've been asked about is this, like, so what's G? What's G? G is equal to 9.81, but if you use 9.8, that's fine as well. Of course, there will be a slight error in calculations, but we're not too concerned with that. We're more concerned with the fact that you know the physics. So if you end up using G as 9.8 instead of 9.81, that's perfectly fine. Okay. The other thing as well is with decimal places, try to stick to the same thing the question does. So for example, question 19, if you look at it, it's one decimal place. It's not always two significant figures. Here we've got 2, here we've got 3. So stick to one decimal place since the question sticks to one decimal place. Anyway, we've worked out the time. So that was part 1. We've worked out the time. What about part 2? We haven't done part 2 yet. So part 2 says, can you work out the horizontal distance, how far it's gone? And that's the easy part because we know that speed equals distance over time. Now I'm trying to work out the distance which equals speed times time, which means I have the time and I have the speed. I have the horizontal speed, which is 3 meters per second. Now, if you prefer velocity times time equals displacement, it doesn't matter. Displacement and distance are exactly the same in this instance because it's a straight line. So 3 times 3.2, which equals 9.6 meters. How far horizontally? So we don't actually need to say direction or anything. It's just asking for magnitude. So 3.6 meters is fine. 9.6 meters, sorry, is fine. Okay, that's how you answer that one. I am going to have to get rid of this. But lucky for you, it's a video, so you can pause it, copy it. But for me, I've run out of space, so I need to rub it all out and drink some tea, I think. Always good. I always tell my students, try and sit in a very quiet environment and get used to just working quietly, like working in a quiet environment with no ambient noises whatsoever. It does make things a lot easier, especially if you're a person who's easily distracted, if you're a person who's got a little bit of hyperactivity. Working in a quiet environment really, really helps. And you can always have a cup of tea as well to make the experience a bit more interesting if you want. Okay, now let's carry on. Question 20 is a similar question to question 19. Once again, we are being asked about how long does the ball stay in the air. Okay, so now we're looking for the time as well. So question 20. A professional football player kicks the football with an initial velocity of v equals 6 meters per second. The I is just x. So that is x, excuse the I. And then 20 meters per second in the y. So we'll just change our I and j to x and y just to make things slightly easier. So what this means essentially is that we have the same situation as before. Okay, but although it doesn't say it's from a cliff or anything, so the question isn't worded properly. But anyway, we've got the x direction over here, which is 6 meters per second, and we've got the y direction, and am I getting this right? Are they? No, it's not being dropped. Oops, sorry, it's not being dropped at all. I'm not focusing. Now this time we've got a field and we've got a ball that's being kicked, and it's a parabola. And what we've got here is you've got the initial y velocity, which is 20 meters per second, and we've got the initial x velocity, which is 6 meters per second. And that's all we've got. And then it says how long will it stay in the air. So this here is called the hang time. So that is what they're looking for. They're looking for the hang time. In order to calculate the hang time, we need three things. Now, we're looking for time, but we need three things to solve the formula, right? So let's say, for example, if we have final velocity and we have acceleration, then we can get somewhere. Now we need the y to solve the time. So we've got, what have we got? We've got the initial velocity, which is 20 meters per second. And you know what? I'm going to say plus 20 because it's heading upwards. And this will become important in a minute. Because you see, I've got the acceleration as well, and that's going to be negative 9.81 meters per second squared. And that's the same as g, acceleration towards gravity. If you prefer, you can write g. Or you can write acceleration gravity, and that satisfies both. And then I also need one more thing, and turns out, lucky for me, I also have VF. Now, how do I have VF? Well, because I've got VI, I know VF, because in a parabola, when things go up, they fall back down, right? We've goes up, comes back down. And turns out the initial velocity is equivalent, exactly the same as the final velocity, just in the opposite direction. And so the final velocity is going to be negative 20 meters per second. Okay, so that's not mk, that's meters per second, and this is meters per second. So I've got 20 meters per second going up minus 20 meters per second going down. So suddenly I've got the three factors that I need. And so once I've got that, I can look at my formula, and I know that Vf equals Vi plus At, right? It's one of the formulas in the formula sheet. And so what I can do is I can go, let's see what I've got. I've got negative 20 is equivalent to 20 plus negative 9.81. Sorry. Negative 9.81 multiplied by t. And so I can once again do some mathematical gymnastics and do this. T is equivalent to, let's just do it slowly because I know some of you will be struggling with this. So if I go minus 20 from this side and minus 20 from this side, then I get minus 40 is equivalent to minus 9.81 times t. And therefore t is equivalent to minus 40 all over negative 9.81. And so therefore, that means therefore, t equals approximately 4.05. 40 divided by 9.81, and that's 4.08 seconds. 4.08 seconds. We found the time. Yay! Once we find the time, we can work out how far horizontally the ball will travel before hitting the ground. Because once again, that's the easy part. It's going to be speed equals distance over time. Distance is equal to speed times time. So I'm looking for the distance or the displacement, and I have the speed. Let's just make it displacement since they give us velocity. I've got velocity times time. Now, somebody might be going, well, hang on, mister. What if I don't remember to use this? What if I use this instead? Can I use that? Well, yes, you can. But remember, with projectile motion, once the object is released, as in this case, the ball is released from the footballer's foot, there is no longer acceleration in the horizontal direction. Okay? There is no acceleration in the horizontal direction. Acceleration only occurs in the vertical direction because of gravity. There is no acceleration in the horizontal direction. It's constant velocity. The moment the ball leaves the foot, it's at constant velocity. And some of the students kind of struggle with that a bit. So once it leaves the foot, it's at 6 meters per second. It will never ever speed up past that on its own. I want you to imagine a situation where you're in outer space and you throw an object or you kick a ball in outer space. The moment that ball leaves your foot, it's going to continue moving at the speed it left your foot, or at the same velocity in the same direction. It will never ever increase in speed on its own or spontaneously. The reason why is because if it did that, if it accelerated even by a small amount, what's going to happen is it's going to reach the speed of light eventually, which is the fastest thing in the universe. I mean, think about it. If something starts off at 2 meters per second, and then after a second it's at 3 meters per second, after another second it's going to be at 4, and so on. Eventually, it's going to continue accelerating until it gets the speed of light. And so every single object on the planet would eventually, every single object in the universe would eventually reach the speed of light if it accelerated once it left the projectile or the initiating projectile, kick or throw. And so just remember, in the horizontal direction, it is constant. Sorry about the rant. Now, moving on. So can I use this? Yes, I can. Absolutely. But what is it going to look like? Let me just change this number, this color. It's a bit depressing. Red? Really? Oh, wow. Did you see these cosmic ones? Should we try one of them? Maybe the ocean one. Let's see what that looks like. Yeah, that's cool. Okay. So delta d is equal to vit plus half at squared. But remember, there's no acceleration. So because the acceleration is 0, so that means this whole thing becomes 0. And so delta t is equal to v initial times t, which is exactly the same as delta d is equal to vi times t is the same as this guy because the v doesn't change. And so delta d is equal to 6 times 4.08, and that equals 24.5 meters. Okay, 6 times 4.08, that'll do. If you prefer, since it's asking for displacement specifically, you can say plus 24.5 meters, and that way you can stay on the safe side. Okay, so that's how you answer question 20. Let's go to question 21. Is there a way to just clear this page without, let me see. I'm not sure. Oh, I can do that. That's cool. But, well, it's not fast enough, but I guess it'll do. Yeah, that's all right. Yeah, sorry, I'm running out of space. And you can always pause the video. Okay, right. What's the next question? The next question looks like it's another one where things fall off cliffs. Oh God, what happened there? How did that happen? Oh, no. Control Z, Control Z. Yeah, that's better. Okay, I'm back to using my. I've got one of these pens and it's got a rubber at the back of it, so that's what it does. It's a Microsoft pen. It's got an eraser, and so it's convenient, but at the same time it's a bit slow. Right, back to this question 21. I hope you're doing these questions with me, because the only way, the best way to learn is to actually do it yourself. Question 21, you crumble up 2 pieces of paper and throw one piece with a horizontal velocity of 2.2 meters per second. At the same time, a friend releases another piece from rest. Both pieces start at 1.5 meters from the floor. So very interesting. How long will it take each piece of paper to hit the floor? So we've got 2 pieces of paper, one that's crumbled up and another that's crumbled up. Now, what's happening here is one is being thrown to the side, the other one is being released directly down. And so what's going to happen is they're both going to fall to the ground, but one of them has been hit to the side, the other one's just been released to fall on its own. Now, hopefully you know by now that since they both have the same speed in the y direction, that means they both fall at the same rate. And that's a difficult concept to get through your head, I understand that. However, they will fall at the same rate. And if you don't believe me, you can watch videos on YouTube about how, like 2 balls, one of them is dropped and the other one is kicked, or a bullet that's shot and another one dropped. You'll see that they both fall and touch the ground at the same rate. The reason for that is because there's 2 components for velocity. One is the x and one is the y. And since they both share the same component in the y, they will both fall at the same rate. That is not being pushed down. Nobody's pushing that down. If it was pushed down, it would be different, but it's just being pushed to the side. The other one is being let go. So they both have the same y component. They will both fall at the same rate. So now that we know that, we can just pick any of these and calculate the time. Remember, it's always the y we're looking for when we're calculating the time. Because of the acceleration, and that's what determines it. So y, let's see, the vi is going to be 0 because it's being let go in the y direction. So let's just pick that, for example. That's easier. Vi, to imagine, that is, vi equals 0. The acceleration is equal to 9.81. I didn't write negative because I'm not going to make the displacement negative either. So the displacement is going to be 1.5, and that way if I make that positive and that positive, then I don't have to worry about the negative signs. Okay, delta D equals VIT plus half AT squared. 1.5 equals 0 because VI is 0 plus half times 9.81 multiplied by t squared. Once again, with the mathematical gymnastics, we go 1.5 all over 0.5 times 9.81. I should write it the way I wrote it before, otherwise some of you might get confused. And that all equals t squared. So t is going to equal the square root of all of that. Now, I've been told that somehow there is a way to make this work on your calculator with shift solve. But I think you have to get to a certain point before you make that happen. So I'm not sure how to make it work. I've not used shift solve. I just do it the boring way, sorry. But if you can work it out using shift solve, by all means, that's fine. Okay, so therefore time is equal to 1.5 divided by 0.5 times 9.81, and then the square root is equal to 0.55 seconds. Now the reason why I wrote 0.55 seconds here is because I'm now going to be using it for part 2. And so here's the thing. You can round up to 0.6 seconds, fine. You can do that, but when you're working out the answer in the next part, it's going to give you errors, right? So you're better off not rounding up just yet. So you can put it up to 2 decimal places. It's fine. Yes, we say stick to the same thing as the question, but we'll accept that in this instance because if you round up, it does give you a bit of an error. Okay. Let's see a different color. Purple, plum, blue. What's that? Dark blue? Indigo. I think I'll go with indigo. Oh, that's lovely. That's beautiful. Okay, so that was part 1. Let's do part 2. How far horizontally does the thrown paper travel before hitting the ground? So once again, we're looking for the horizontal distance in this instance for this guy here. Now we know that the horizontal speed was 2.2 meters per second, and so delta D is equal to 2.2 multiplied by the time, which is going to be 0.55, and that equals approximately 1 point something, 1.2 maybe, 2.2 times, no more than that, 0.55, 1.21, 1.2 was fine. Okay. Yeah. So in this case, it doesn't ask for displacement, so we can just give the magnitude, and that will be the answer. Okay, so with this sort of question, first work out the time, okay, and then work out the distance using simply distance equal speed times time. Let's move along. Yay, graphs. A professional baseball pitcher throws a baseball horizontally across a field. The graphs show velocity versus time in the horizontal direction and the vertical directions. What is the total horizontal displacement? Of course, in this instance, we should know hopefully that displacement is equal to the area under the graph. And if you don't remember that, and hopefully you still remember the formula, displacement equals velocity times time, right? So this is the velocity over here, and this is the time. So it's velocity times time, which is rise times run, or the x times the y. And it's the area under the graph. Okay. So with that in mind, question 1 says, what is the total horizontal displacement? Dx. So this represents dx because you can see the x in there, and that represents, and this here represents the y. So for the x, it's going to be 40, which is the velocity, multiplied by 0.5, which is going to be plus 20 meters. Now, the way I write plus is because it has direction and it's displacement. So plus 20 meters. What about number 2? What is the total vertical displacement of the baseball during 0.5-second motion in the y direction, that is? So delta d in the y is going to be v times t, or vy times t. So it's going to be -5, because I can see here that it's -5 multiplied by 0.5, and that equals, oh, hang on, all over 2. Why all over 2? Because remember, it's a triangle this time. And the area of a triangle is half base times height. Okay, the area of a triangle is half base times height. So 0.5 times 0.5 divided by 2. And that's going to be -2.5 all over 2, so -1.25 meters. Okay, and once again, the negative denotes the fact that it's displacement and that it's a vector and has a direction. Question 23. A tank fires a shell with an initial velocity of 100. So once again, this represents the x, and this represents, why do you do that? Why do you erase yourself? And this represents the y. How long will the shell stay in the air for? So hopefully by now you understand that the shell has a parabolic path. The shell has a parabolic path, and therefore the y on this side equals the y on this side. So 52 up, -52 on this side. So I have VI and VF. I also have A, which is -9.81. And so I can do this. VF equals VI plus AT. So that's going to be 52 is equal to -52. What did I do here? Yeah, right? Plus AT. Oops. Plus -9.81 times t. So it's going to be -104 all over -9.81, and that equals t, which is approximately 10 seconds. 104 divided by 9.81 is 10.6 seconds. Now here's a little bit of a hint. If you do this and it comes up with a negative time, just change it to positive. You can't have negative time. So if you do this and it comes up with a negative time, just make it positive. Okay. 2. What is the maximum horizontal distance traveled by the shell in kilometers? Make sure you read the question carefully. So once again, delta D is equal to velocity multiplied by time, which is going to equal 130 multiplied by 10.6, which is a little bit over 1,400 meters, or 1.4 kilometers, 1.4, 1.5 kilometers. 1,378 meters, or 1.4 kilometers. Okay, that's how you do that. Question 24, I'm going to do over here because I don't feel like rubbing all of this off. It's pretty easy, actually. If you get a question like this in the exam, they like just fun marks, easy marks, really. So centripetal acceleration is equal to v squared over r, which equals 5 squared all over 2 meters. and that equals 12.5 meters per second squared. That's how you answer that one. It's simply the formula. Okay. Question 25. I'm going to need some space for that, so I'm going to make some space for it. I'm going to take all of this off. Okay. Guess that will do for now. That's enough space. Okay. I'm going to draw a line as well. Nope. Don't take yourself off. Okay. A child is riding a merry-go-round that has a radius of 4 meters. So if the child is moving at a velocity with a velocity of 3 meters per second, what is the centripetal acceleration? Okay, so centripetal acceleration is equal to v squared over r. So that's the formula. The workout is going to be 3 meters per second squared all over 4 meters. So that's 9 over 4, which is 2.25 meters per second squared, 2.25 meters per second squared. The second part of the question asks for if the merry-go-round needs to be adjusted so the child experiences centripetal acceleration of 2 meters per second, what should the new velocity be? Okay, so I'm assuming they don't want to adjust the radius. So AC equals v squared of r. We have the same radius. We have the centripetal acceleration. So we have centripetal acceleration of 2 meters per second squared. And we have radius of 4 meters. That's just from the question. And what should v be? So that's going to be 2 is equal to v squared over 4. And so v is equal to 2 times 4 equals v squared. And so therefore v is equal to the square root of 8, which is approximately 2.8. 2.8 meters per second. Velocity, so plus 2.8 meters per second. Okay, question 26. We're not doing too badly. We're getting through it. Hopefully you're not finding these too hard. Let's have a look. Question 26. 1,800 kilogram car has an acceleration of 3.8. What is the force acting on it? Oh, lovely. Easy peasy lemon squeezy. So that's force equals mass times acceleration. So it's 1,800 multiplied by 3.8, which equals. Hopefully, you don't overthink like I do, because sometimes students overthink questions in the exam and they think, oh, there must be a trick somewhere. It can't be that easy. Hopefully that doesn't happen to you. Yeah. Right. That's question 26. Let's go to the next one. Oh, this question has an issue. Right. I'm going to change the question. I'm going to make it make sense because this one has an issue that was pointed out to me by my colleague. So let's have a look. A 71 kilogram parent and a 19 kilogram child meet at the center of an ice rink. They place their hands together and push. What is the force experienced by the child? Well, if the question is given to you the way it is without the force that I've just drawn, without this, it doesn't make sense. You couldn't work it out. But if I add this force here, then suddenly the question makes sense. There's many ways for the question to make sense, but I just chose that. Where did you get the 100 from? From my head. So here we go. What is the experience? What is the force experienced by the child? It's going to be exactly the same, equal and opposite. So if we say that's 100 in that direction, then the child is going to experience 100 newtons in the opposite direction. And so if that's, say, for example, positive 100, then it's going to be negative 100. But I don't know if that's positive and that's negative. So I'm just going to say, I'm just going to say 100 newtons in the opposite direction. Um, in the exam, though, it'll be very clear. Like it'll say 100 newtons to the left. So then you'd say 100 newtons to the right. Yeah. Number 2 says, what is the magnitude of the parent's acceleration? So force equals mass times acceleration. We know the force is 100. We know the mass is 71. We don't know the acceleration. The acceleration is going to be 100 over 71, which is 1.4 something. 100 divided by 71. 1.4 meters per second squared. Question 28. Your 1,400 kilogram car pulls 560 kilogram trailer away from the stoplight with an acceleration of 1.85 meters per second squared. What is the net force exerted by the car on the trailer, and what is the net force acting on the car? A very good question indeed. Okay, so let's think about this carefully, because this is the kind of question that students can get wrong because they kind of underestimate what's involved here, or they think of the wrong components to use. So let's see. Let's draw the situation. So we have a car. And the car is pulling the trailer. The trailer has a mass of 560 kilograms. And the car has a mass of 1,400 kilograms. They both accelerate at 1.85 meters per second. Squared. Now, what is the net force exerted by the car on the trailer? Okay. We know that force is equal to mass times acceleration, but what kind of mass are we using here? Are we using the mass of the trailer? Are we using the mass of the car? Or are we adding them together, the mass of the car and the trailer? Okay. So in order to answer this question, I want you to imagine a situation where, let's say, for example, there is a door. Okay, there's the trailer. Oh, I'm not going to use a trailer. I'm going to use a different example. I'm going to use a person. And the person is sitting down on the floor. And the person is sitting on a skateboard. And they're being pulled by a rope. And that rope goes around the corner. And they can't see who's pulling them, right? They can't see who's pulling them. But that rope goes around the corner. So there's the door. There's the door over here. The door to the classroom. And then there is another person pulling from here. Okay. That's the person pulling this person. Now, if they pull this person with 1.8 meters per second squared, then that person is going to experience a force, right? Okay. What if I replace this person here, and instead of putting person like small person, what if I put an elephant, a big massive elephant? Okay. A big massive elephant, and they are pulling the person now with the same acceleration. As long as the elephant is pulling with the same acceleration, this person here is going to experience the same force. The weight or the mass of the person pulling isn't going to make a difference. The mass of the animal isn't going to make a difference. And so likewise, this example here, the car is pulling the trailer. The mass of the car is irrelevant. We don't care about the mass of the car. It's only the mass of the trailer that matters, right? Because the trailer could be being could be pulled by a motorbike, could be pulled by an elephant, whatever. It doesn't matter what this mass is, as long as the acceleration here is 1.85, the force is going to be the same. So it's going to be 560 multiplied by 1.85, and so the acceleration is going to be 560 multiplied by 1.85, which is 1036 newtons. That's what the net force on the trailer is going to be. Question 2, however, is slightly different. It says, what is the net force acting on the car? Now, let's draw a free body diagram. Remember, a free body diagram is a diagram that shows the forces acting on an object. So this time we've got the force forward, which is basically the thrust or the engine of the car. And then we have something else. For the trailer, it was just the pull force from the car. But for the car, there is another force acting backwards, which is hindering the car. So we've got the force of the car, which is, F equals ma, so 1,400 multiplied by 1.85. Now that equals 1,400 multiplied by 1.85. That equals 2,590 newtons. But that's not the full story. We want the net force. That would be okay if the car wasn't pulling a trailer. If the car was just going on its own, that would be the net force. But there is a trailer that is slowing it down because it's pulling the weight of the trailer as well. So what is that? What is that force? Well, we just worked it out. That's the force. So what we're going to do is we've got 1,036 newtons in the opposite direction. So the overall net force is going to be the force of the car minus the force of the trailer, which is going to be 2,590 minus 1,036. And that's going to be 2,590 minus 1,036. And that's going to be 1,554 newtons. And if you prefer, you can say positive. That way you can be sure that it's not so confusing, I guess. Okay. Not so bad, I hope. Let me get rid of some of this stuff. Right. The next question asks about ducks and geese. But once again, I feel like there's a bit of a problem in the question, so I'm going to try and fix it. Right. I want you to do this. First of all, that says a goose of mass 3 kilograms is swimming with a velocity of 1.3 meters per second in the positive y direction. We're going to change the y here and make it x. And then the other thing as well is it says a duck of mass 1.5 is swimming with velocity of 1.1. We're going to change a to 2 ducks. And also is swimming to are swimming because we care about proper grammar. So a goose of mass 3 kilograms. So just like the picture, really. So we've got a 3 kilogram goose and then 2 ducks that are 1.5 kilograms each. And we're trying to find out the momentum. Okay. So let's have a look. I'm going to get rid of this as well. And just to make some space and just make things easier and hopefully not so confusing. Okay, here we go. So question 29. What is the momentum of the goose? To begin with, the momentum of the goose is going to equal momentum, or change in momentum is equal to mass times velocity, which is, now here's the thing, momentum is actually a vector quantity, which means it has direction. Momentum, force, acceleration, displacement, velocity, all of them are vectors, so they have direction. So momentum is equal to mass times velocity. We know the mass of the goose is 3, and we know the velocity is 1.3. So it's going to be 3.9, and I'm going to say plus 3.9, or 3.9 in the positive direction. But there is also a unit, which is kilograms dot meters per second. The way you remember the units, the way you remember any units, is by looking at the formula. This is mass, which is kilograms. This is velocity, which is meters per second. And so it's kilograms dot meters per second. That's the unit. Kilograms dot meters per second. What is the momentum of the duck? Okay, it says one duck, but that's, let's just see. Momentum of duck. So I'm going to start doing things properly. That is momentum of goose. This is momentum of duck. It's going to be mass times velocity, which is 1.5 multiplied by negative 1.1. Why negative? Because it's in the opposite direction to the first one. Now, if I didn't do that, I would get the momentum, but it would be the magnitude of the momentum without the proper momentum, without direction. So I wanted to make sure that you understood that it's in the opposite direction. And so I get something like 1.6, 1.7, 1.5 times negative 1.1, and that is negative 1.65 kilograms dot meters per second. Now I have the momentum of one duck and I have the momentum of the goose. The third question asks me calculate the momentum of the entire system, the goose plus the ducks. Okay, so it's going to be total momentum. This just means total momentum equals the momentum of the duck minus, oh sorry, the momentum of the goose. I'll start with the goose, minus the momentum of the duck minus the momentum of the second duck, because there are two ducks. And so it's going to be 3.9 minus 1.6. Now, some of you might be going, well, hang on, it's minus minus, right? So it's literally just adding, sorry, it's adding all of them. That's what I need to do. I need to add all the momentums together. But when I add them, I'm subtracting them because they're negatives. So I'm sorry about that point. I just need to make that clear. When you're doing momentum of the system, you're just adding all the different momentums. But this is what you're going to notice now. When I'm adding the momentum of the duck, I'm subtracting because it's minus anyway. So sorry, I just did that in my head, and I should have explained it before doing it. So that's what happens, is that you just add all the momentums, and so you end up with 0.6, is it? 3.9 minus 1.65 minus 1.65, 0.6, or positive 0.6 kilograms dot meters per second. Okay. By the way, it's always a really good idea to just like have a group, or at least one person that you bounce ideas off, work through this with them, and ask each other questions. If you don't understand it, then you can ask someone else. Um, and finally, like if you go on, say, Google or Chat GPT, and you still can't find the answer, you ask your friend, you still can't find the answer, you ask someone else in the classroom and you still don't know the answer, then that's when you should ask your teacher. But do give yourself a chance. Struggling is good for you. um, Struggling to find the answer is going to help you retain the information. It's going to make you remember it. It's actually a workout for your brain. That's how you learn, really. Pain is gain, as they say. Okay. um should we carry on? It's getting a bit long, this video. Question 30. A designer is determined to type the type of wire to use for a pendant light hanging from the ceiling of an elevator. The wire can withstand a maximum force tension of 70 newtons before breaking. The lamp has a gravitational force weight of 60 newtons acting downwards. The lamp has a mass of 6.1 kilograms. What is the maximum upward acceleration of the elevator can have before the wire breaks? Okay, so this is not the sort of video where I'm explaining concepts in great detail. If you want to know like a certain concept in greater detail, please go back to the original videos. which I do have. For now, though, I'm just explaining things in little detail and I'm solving the problems. And I would advise if there is a problem with one of the topics, if you're not sure about one of the topics, that's when you go back to the original videos. Okay, let's have a look. What we have here is we've got a light bulb, a light hanging inside an elevator, and as the elevator accelerates upwards, it experiences a bit more tension. I want you to imagine a situation where, let's say, for example, this is the example that I used in class. So I'm just going to repeat this example. Some of you are familiar with it now. I'm going to use a hair and I'm going to tie the hair around a banana. Okay, so I've got a banana, okay, and I've got a hair. No, not like that. I've got a hair tied around the banana, and it's a very fragile, very delicate human hair tied around a banana. And I challenge you and I say, you know what, could you lift the banana without breaking the hair? Now you can do that by lifting the banana, but you're going to lift it very carefully. The reason why is because you don't want to accelerate it upwards too fast. The more acceleration it experiences, the more force that hair is going to experience, and the easier for the hair to break, right? So we know that concept. We know that if I accelerate the banana, if I take that hair and I lift it up quickly, it will break the hair and I would lose the bet. So what I need to do is lift it up slowly, right? Now this is very much the same concept we have over here. So we have an elevator. There is the wire inside the elevator, and that wire is holding the light bulb. And so if I accelerate upwards too fast, then that tension is going to break the wire because it can only withstand 70 newtons. So if I look at the body diagram, there is a weight force down of 60 newtons, okay? 60 newtons. That's what it says anyway. And there is a tension force up, a maximum tension force of 70 newtons. And this here is the apparent weight, because remember, apparent weight is equivalent to normal force or the upwards force or tension force. So that is the maximum. And so if I look at the formulas that I have, I've got F apparent is equal to mass times gravity plus or minus A. Plus or minus acceleration. Now, some of you prefer this. Okay, that's fine. They're exactly the same. So we have 70, which is the maximum, and that's going to equal the mass of the bulb, 6.1 kilograms from the question, multiplied by 9.81, and now I have to determine whether it's plus acceleration or minus. Now, remember, acting downwards, lamp has, what is the maximum acceleration? Upward acceleration. So it's going to be plus the acceleration, because obviously I have to add the acceleration. It's going to experience more acceleration. As I'm pulling upwards, okay, that rope, okay, that cable is going to experience more acceleration. Okay, so that's going to be plus the acceleration, and that's going to equal 70. So it's 70, first of all, divided by 6.1 is equal to 9.81 times A. No, plus A, sorry. And so it's 70 over 61 minus 9.81. That equals A. Therefore, A is equal to 70 divided by 61 minus 9.81. Minus 9.81. And so the maximum acceleration is approximately 1.67 or 1.7 meters per second squared. Okay, that's how you do that. Now, I just want to make a point here. If you are standing in an elevator, your weight is going to equal mass times gravity, especially if the elevator isn't moving or if it's moving at constant speed, which is during the middle portion of its journey. However, at the start of the journey, depending on when if the elevator is going up or going down, you're going to experience a different weight, right? And that's because the floor of the elevator is either pushing up against you or kind of falling under you. So if it's going downwards, if you're up on the third floor and the elevator is going down, accelerating downwards, you're going to feel lighter. And so that's when you say minus A. But if you're on the ground floor and the elevator is traveling upwards, then that floor is pushing up against you. And so you're going to feel heavier. And so you add the acceleration. So you go G plus A. Okay? So it all depends on which direction you're traveling that makes you feel a different way. Okay? Let's go to question 31. Question 31 says two dogs that are pulling on a rope. One of them has a mass of 12, the other one has a mass of 18. What is going to be the net force, I think? What is it asking for? Let's have a look. I've got a dog over here, and I don't know how to draw dogs. Maybe? No, they have front folding, right? Front folding legs? Back folding legs? I don't know. Here's my first dog, and here's my second dog. And here we go. I should look up how to draw dogs. Anyway, so that one is pulling this way, and this one is pulling that way. This one has a mass of 18 kilograms, and this one has a mass of 12 kilograms. This one pulls with 12 newtons, and this one pulls with 12 newtons. It's a trick question, is what it is. Because, quite frankly, I couldn't care less about the masses of the dogs. All I care about is the force. What is the force it's pulling with? So to determine the net force, it's going to be 12 minus 12, so it's going to be 0 newtons. That's the net force acting on it. So I'd write force equals 12 minus 12. So F net is going to equal 12 minus 12, which equals 0 newtons. And the next one says, what is the acceleration of the rope? Well, first of all, in order to work out the acceleration of the rope, I need the mass of the rope, which is not even given to me. I'm given the mass of the dogs. The other thing is I'm not going to experience any acceleration because the force is equal to 0. The net force acting on the rope is 0. It's balanced. So therefore, the acceleration is actually 0. There's no acceleration. Okay, there you go. Question 32. What is the overall net force acting on the box? Good. My grade 8s could do this, actually. So it is going to be 50 newtons to the right. Okay. Number 2 says, if the box has a mass of 25 kilograms, what is the acceleration? So now I know that the force is equal to 50 newtons, and the mass is equivalent to 25 kgs. So the acceleration is obviously going to equal 2. But in case you're wondering how I got that, it's going to be 50 is equal to 25 times A. Therefore, the acceleration is going to be 2 meters per second squared. And number 3 says, how long will it take the box to travel 10 meters if it starts from rest? Nice. So delta D equals 10. What else do I have? VI equals 0. Acceleration equals 2. That's enough. Delta D equals VIT, which is 0, plus half AT squared. So it's going to equal 10, 0 plus half times 2 times T squared. So T is going to equal the square root of 10. Just believe me on that. Which equals 3.16 seconds. That's how long it's going to take. Okay. Should we keep going? Should we stop? Yeah, I think I'll stop there and I'll do another recording later. But you won't feel any of that. You'll just see me in different clothes. That's all. See you soon. See you in a second. Okay, hello again. Okay, we're going to be continuing with question 33. You are handed a spring that is initially 0.3 meters long. So that's the resting length of the spring. You hang the spring from a hook on the ceiling and attach a zero point 0.5 kilogram mass to the other end. The spring stretches to a total length of 0.35. What is the change in length? The change in length is going to be the final length minus the initial length. So that is going to be 35 centimeters minus 30 centimeters, or 0.35 minus 0.3 meters, which is equal to 0.05 meters. Question 2 asks, what is the weight of the attached mass? So the weight is equal to the mass times gravity, which is equal to 0.5 multiplied by 9.81, or 9.8 if you prefer, which is going to be approximately 5 newtons. 4.9 newtons. Okay, and what is the spring constant of the spring? So this time we have to look at the formula, and the formula states that the spring constant is going to equal, so force is equal K times delta L, right? Spring force to be specific. Now we know that the spring force is going to be equal to 4.9 newtons because that's what's pulling the spring, and that equals K multiplied by 0.05 because that's the stretch, right? So K is going to equal 4.9 all over 0.05, which is very close to 100, which is 98.1. And of course, newtons per meter. Okay? Right, let's look at question 34. Different weights are being hung on a spring. Let me just go down a bit. Yeah. Different weights are being hung on a spring, and the diagram shows the original length of the spring, which is 15 centimeters, and then the length of the spring when different weights are added. Okay. The extension of the spring is directly proportional to the weight hung from it. What is the spring constant of the spring? Okay. So there are two ways of calculating. Actually, we have to use the middle one, don't we? Because that's the only one with actual weight force. So we have to use that. So if we use the force as 20 newtons, and then we have the stretch, which is delta L, and that's going to equal 0.25 minus 0.15, which is 0.1 meters. Because remember, the length has to be in meters, so that's why I'm converting 25 centimeters to 0.25 meters. Okay, and 15 centimeters, 0.15 meters, and 35 centimeters, 0.35 meters. How did I convert from centimeters to meters? All I have to do is go 35 divided by 100, and that will give me the answer in meters. So anyway, I've got the length, I've got the force, so I can work out K. So K is going to equal force all over change in length, which is going to equal 20 newtons all over 0.1, which is equal to 200 newtons per meter. Okay, and question 2 is asking about if the spring extends to 35 centimeters, when a weight W is hung, calculate the value of W. So now that we've worked out K, we can work out what W is going to be because, well, that's just going to be the force, isn't it? The force is W, which is equal to K multiplied by the extension, and it's going to be 200 multiplied by the extension. Now the extension is not 0.35. The extension is 0.35 minus the resting length. So it's going to be 0.2 meters, which is 40 newtons. Okay, so that's the answer to that one, 40 newtons. Um, there is another way you can do it, and you can do it using proportionality. Um, and you can do it that way. It's perfectly fine. So if you work out the difference in length between this and then the difference in length between this, and you can divide across both and multiply by 20. So what I mean by that is this. So some people might feel comfortable doing that. Okay. Um, so that's the first one, but then we want the next one. So zero, so you can go 35, sorry. 35 minus 15 all over 25 minus 15 multiplied by 20, and that will give you the same answer, which is 40 newtons. So this is the mathematical way of doing it through proportionality, which is just dividing the first length by the second length or the last length by the original length and then multiplied by the weight. Doesn't matter. It doesn't matter. Both of you give the same answer. Okay, I personally prefer that because you can see where you go wrong if you do. Anyway, let's keep going. Um, okay. Okay, let's carry on. Question 35 says a dog is pulling an empty. Let's see if this actually still works. Yeah, it works. A dog is pulling an empty sled attached by a harness parallel to the ground in the snow. The sled is moving with a constant velocity. The mass of the sled is 1.2 kilograms and the coefficient of static friction is 0.2. So the coefficient of static friction means this here, mu s. What is the gravitational force acting on the sled? So when they're asking for gravitational force, really what they're asking for is the weight. So because it's a force, right? They're asking for gravitational force, and gravitational force is equivalent to weight, Newton's force. So that's what they're looking for. So question one, what is the gravitational force acting on the sled? Well, hopefully you remember that the weight, or this time the force, is equal to mass times acceleration, and the weight is equal to mass times gravity, right? So it's going to be 1.2 times 9.81, which is equivalent to approximately 11, 1.2 times 9.81, which is equivalent to 11.8 newtons. Okay, 11.8 newtons. Question 2 asks, what is the frictional force acting on the sled? So hopefully you also remember from your physics, and if you don't, obviously you should use the what is it called, the formula sheet. Okay, so hopefully you remember that Fs, which is the frictional force, or sorry, not Fs, you'll use frictional force, which is this guy here, is equal to mu, and it depends whether it's static friction or kinetic friction. So, but we'll just use static friction here. Mu s multiplied by the normal force. Okay, because there are two variables that control the friction experienced by an object. And the first variable is going to be the material. So the material that decides the friction, that's what this is for. That's what mu s is for. That's different for different materials. So it depends on the material, while the normal force is what decides how close the two objects are. So if, for example, I'm going to measure the friction between my hand and this book here, okay? So obviously there is friction there, right? And that can be defined by mu s or whatever it is. But then if I apply more force, so my hand is like really pushed against the paper, then it's going to have more friction than if it was quite loose there. So that's why the normal force and the friction coefficient are both important. Anyway, back to the question. So what is the friction force here? It's going to equal 0.2 multiplied by the normal force, which we found earlier. So that's going to be, because weight is equivalent to the normal force in this instance. Like, remember, if a box is sitting on a table, and it's experiencing weight force downwards and experiencing normal force upwards. And these two are equivalent because there's no acceleration in the vertical direction or in the y direction. Um, okay, so that's going to be 11.8, which equals, well, back to 0. No, 2.3 maybe? Yeah, so approximately, yeah, 2.4. I would say 2.4 kilograms. Oh no, not kilograms, newtons once again, sorry. I need my coffee. It's coffee today. Well, now, this portion of the video, it's coffee. Okay. Question 3. Determine the tension in the harness. So the way we answer this is, let's see. So we're assuming it's completely, there's no other force acting on it besides the friction force. So this is a hypothetical situation, really. Like in real life, you wouldn't have this. But let's just work with the hypothetical situation in the question. There's no applied force. There's no other forces besides the friction force. So the only thing that is determining the tension in the string or in the rope is going to be the friction force. And since it's going at constant velocity, it means that these forces are balanced. So this is the friction force over here, and over here we've got the tension force, and obviously they're going to be balanced, so they're going to be equal. So the tension force is going to also equal 2.4 newtons in size, at least. So it's going to be equal in size and magnitude, but it's going to be the opposite direction to the friction force. Okay, and that's how we do that one. Right, let's go to question 36. A large painting is hanging motionless from two wires attached to the same point at the top of the frame. The wires are attached to equidistant points. So equidistant just means equal distance. Equi means equal in Latin and many of the Latin languages. And distant is distance. So points on the wall above the painting. Each wire has a tension force of 108 newtons in the y direction and 80 newtons in the x direction. Okay, let me just draw what that looks like. And I'm going to draw it kind of in 3D. Just helps visualize it better. Okay, so here is the frame of the photograph. And here is the inside. Taking my time with this. And it's going to be mountains, the Alps. Okay, in fact, there's a wee bit of a lake there, and there is a boat. Here we go. So what they're saying is there is a ring here or something at some point to attach the two strings. That's what we're looking at. And at this stage, I would like to change the color. And we're going to go with, let's try green. So what they're saying is in the x direction, there is 80 newtons. You see, 80 in the x. And in the y direction, there is about 108 newtons worth of tension. So they haven't told us the overall tension in the rope, but you can work it out if you want to. The question doesn't ask for it. If the question was asking for the tension in the rope, because forces are vectors, we can find the tension in the rope using a squared equals b squared plus c squared. So we'd square that, and then find the square root, and then we could find the tension in the rope. But that's not what it's asking for, so let's not get carried away. What the question is asking for is the vertical tension. The vertical tension in the rope is going to equal only the vertical aspect, so only the y's. So it's going to be 108 plus 108. Okay? Vertical tension, I'm just going to write it this way. Vertical tension in the y is equal to 108 newtons times 2, which equals 216 newtons. Okay? That's what that is. And part 2, determine the mass of the painting. Well, if I've got the vertical tension, which is the force pulling up, then I know that the weight force going down is exactly the same. So it's 216 newtons up. It's going to be 216 newtons down. That is the weight. I want the mass. So I'm going to go back to this guy here. Weight equals mass times gravity. And let's see, weight equals mass times gravity. Well, I have the weight, which is 216, and that equals mass times 9.81. So the mass is going to be 216 divided by 9.81, which is approximately 22 or 23. 9.81. And that's going to be 22 kilograms. Now, once again, if you're unsure about decimal places, as I said, like look at the question, it's one decimal place, whatever. But if you're not sure, just go to 2 decimal places. Okay, don't go more than 2 decimal places. And only do that at the end, right? Okay, so I'm running out of space and I'm gonna need this space, so I'm going to spend the next 30 seconds rubbing all of this off. Normally in the classroom, I will always have someone say, "No, mister, don't rub it off. I'm writing it." The good thing about videos, once again, is that you can pause it, go back, freeze, frame, catch me doing a funny face. You can do all of that with a video, which is great. Right. This is taking ages. Okay, and I hope that you are doing these at the same time I'm doing them. You really have to have a pen in your hand and a calculator. Always have your calculator with you. This is my old calculator, the same calculator I've used when I was in school. I've had the same calculator for 20 years, more than that. Yeah, 25 years now. Yeah, back when I was in school. So 25 years, same calculator. It's been absolutely wonderful to me, and I've taken care of it, and it's taken care of me. So yeah, look after your calculator. Right. Let's see. Question 37 now. Question 37 says, a child is pulling an empty cart attached by a rope that is parallel to the ground. The cart is moving with a constant velocity. So once again, we have balanced forces. We don't have acceleration because it's constant velocity. And its mass is 1.5 kilograms. Suppose a mass of 7.5 kilograms is added to the cart. What's going to happen if the velocity stays the same, basically? What is the initial tension in the rope? So we already know from the previous problem that we've done that's similar to this problem. Since the sled is parallel to the ground, and since in this case there is no friction, at least in the previous problem there was friction, but in this case there's no friction. So the only thing that's causing the tension is the weight, or the weight of the sled. Again, this is a hypothetical situation, so they don't even talk about the applied force. So all we have is the 1.5 kilogram sled, okay, and yeah, so it's going to be, the tension is going to be equal to 1.5 multiplied by, because that's the only force we have. So mass times gravity times 9.81, and that's going to be approximately 14.7 newtons. So that's basically what the tension is going to be. It's going to be equivalent to the weight, more or less, in this hypothetical scenario with no friction forces whatsoever. Okay, part two. What's going to be the final tension in the rope after adding 7.5 kilograms? So this time we've added 7.5 kilograms. So on top of the 1.5, we've also added 7.5, which makes the total mass of the sled now 9 kilograms. So since the mass is 9 kilograms, the weight is now going to be 9 times 9.81. Okay, 9 times 9.81, which is equivalent to 88.3 newtons. And that's going to be the tension. Okay, so that's the new tension. And number 3 says, by what factor does the tension in the rope change? So all of this question, the whole point of the question is to show you that tension in the rope is going to change in a linear fashion with relation to the weight. So basically, if you double the weight, you double the tension. You triple the weight, you triple the tension, and so on and so forth. So what we've done was we made the weight 6 times, and therefore, if you notice, we have also made the tension approximately 6 times. So the tension has become 6 times as the result of the mass being 6 times and the weight being 6 times the weight. Okay. I'm going to take all of this off because the next question requires me to draw a free body diagram. I can just tell because of the boxes, and hopefully you guys remember how to do that. If you don't, then pay close attention while I attempt to do it. Let's have a look. Should I change the color? Sure. Change the color to blue. Did I tell you I was colorblind? I'm going to go with that. I hope that's blue and not light purple. Let's have a look. Question 38. Oh, that's like sky blue. Teal, I think they call this. Anyway, a push force of 40 newtons is applied to 3 boxes of equal mass. They are 2 kilograms each. 2 kilograms each, 2 kg, 2 kg, and 2 kg. Okay, aligned in a row on a frictionless surface. Calculate the acceleration of the system. So that's the easiest thing. I love when they say calculate the acceleration of the system, because all I have to do is go F net equals total mass total, multiplied by acceleration. Okay, so we're trying to find this guy, and we have this, and we have this. So obviously acceleration is equal to force over mass, net force over total mass. So in this case, it's going to be 40 newtons, as it is over here in the question. And the total mass is going to be 2 plus 2 plus 2, which is 6 kilograms. And that equals 6.67 meters per second squared. That's what that equals. Okay. Question 2 says, determine the force exerted by box C on box B. Okay, so this is when we have to do some thinking. What I'm going to do here is I'm going to draw the free body diagram. The free body diagram, remember, is a diagram that shows the forces acting on an object. Okay? And what we have going on is we have a situation where we've got the applied force acting on A, and then we've got another force acting on A, and that is, this is A, this is B, and this is C. We've got the force of B acting on A, but we also have a force of A acting on B, which is exactly the same, just in the opposite direction. And then over here, we've got another force. What is this force? It's going to be force C acting on B. And then we've got force B acting on C, and those are the forces that are happening here. Now, if I put some numbers on them, that's going to be 40. Now, what's force B acting on A is going to be? Well, that one here. Well, this force here is going to equal the mass of both of these pushing on A. Because remember, box A over here, okay, is pushing both B and C. So this contact force over here is going to be both of these boxes pushing back on A. So the force of B on A is actually the force of C and B on A. So that's going to be mass times acceleration. We know the acceleration, but it's going to be the mass of B and C. So it's going to be 4 multiplied by 6.67. That's from there, from the previous question. And that's going to be 23 point something. 4 times 6.67. Sorry, that's 26.68 or 26.7, let's say, 0.7 newtons. But what I'm going to do is I'm going to say minus 26.7. The reason why I'm saying that is because it's in the opposite direction. So really, if you want to be pedantic, you could have made the acceleration negative 6.67 for that portion. But I'm not worried, it's just in the opposite direction, so make it negative. So that's negative 26.7. This is 26.7 because they're equal and opposite. And we're going to take this way as this way. Wait, no, this way. This way. No. Okay, let's see which way is it facing. We're going to take this. No, that. Yes, we're going to take that as positive. This as positive. That as negative. Very good. Okay, so this is positive, that is negative. That's just so much easier if I had drawn it instead of just trying to do that with a pen. Silly me. Anyway, the force of C on B, so hopefully you can do that. Obviously, that's this guy here, okay? This is only C, not anything else. So it's going to be 2. So the force of, that's B on A. And so here the force of C on B is going to be the mass of C multiplied by the acceleration, which is going to be 2 times 6.67. And that's going to equal, once again, it's negative 13.3 newtons. So that's negative 13.3, and that's 13.3. Okay, so what is the force exerted by C on B? So that's going to be 13.3 newtons backwards, or if you want to say to the left, if you want to, or opposite to the applied force. Okay, it doesn't matter as long as you indicate some sort of direction. Okay, and in fact, yeah, so you can even use a negative, it's fine. But that's how you do that. Okay, let's move on. Oh, we're nearly there. A 70 kilogram person, let's change the color. I think this warrants changing the color once again. Plum, let's go with plum. Let's try plum. Oops. Why are we all the way back up now? Come on. Here we go. We've done that. Here we go. A 70 kilogram person rides an elevator that accelerates upwards at 3 meters per second squared. At the start of the motion, determine the apparent weight of the person. Right. So we've got a person that's going up. So obviously the elevator floor is pushing up against them, which makes them feel what? Heavier or lighter? It makes them feel heavier, doesn't it? So the elevator is accelerating up and it's pushing up against them right at the beginning. I want you to imagine yourself in that scenario. You're inside the elevator. It's pushing up on you. It's pushing up against you. So what's going to be your apparent weight? Well, if you look at the formula sheet, your F apparent is going to be, oh, that's terrible, is going to be mass times gravity plus or minus acceleration. Now, because the person is actually going up and they feel the force of, what's it called? The elevator floor pushing on them, it means they're going to feel heavier. So we add the acceleration. So it's going to be 70 kilograms multiplied by 9.81 plus 3 meters per second. And that will make them feel like they are maybe about 100. 70 times 9.81 plus 3. Oh, I was going to say about 1,000. It's actually 897 newtons. There you go. Okay, if you want to write 896.7, that's fine. If you want to write 897, that's fine. Don't worry about semantics. So that's correct. If you round, as long as you rounding correctly. So that's question 39. Let's go to question 40. Question 40 states a sandbag of mass MB equals 20 kilograms is connected to a dolly of mass MD equals 30 kilograms. Using a pulley system, the system is on a frictionless surface. Frictionless surface, that means you don't have to worry about friction. Always a bonus when you don't have to worry about friction. Calculate the acceleration of the system. So hopefully you remember by now, in order to calculate the acceleration of the system, I need to find the applied force first, which is going to be that. That's the only source of applied force, the weight of the bag, isn't it? There's nothing else causing the system to accelerate except the weight of the bag. So let's find the weight of the bag first. So the applied force, the force applied, is going to be the weight of the bag, which is going to be, weight of the bag is going to be 20 kilograms multiplied by 9.81, which is approximately 196. 196 newtons. So once I've found that, the next step is to find the acceleration. Acceleration is going to be F net, which is the applied force. F net is equal to the applied force here because we have no friction. So F net is equal to the applied force divided by the mass of the system, the mass, total mass, which is going to be the 20 and the 30. So it's going to be 196 newtons divided by 50 kilograms. That's going to be 3.9 meters per second squared. So that's the answer to that. Question 2 says determine the tension in the rope. So the tension in the rope over here is going to be equal to mass times acceleration. Tension is equal to mass times acceleration. Mass times acceleration, and so it's going to equal 30 kilograms multiplied by 3.9. 30 times 3.9, and that equals 117 newtons. Now, there's another way to find the tension as well, because remember, tension is the same across the whole rope. If you're not sure about this, please watch my video on forces on systems. But I can work out the tension using the weight. So tension is going to equal it's going to be the apparent weight, isn't it? Because this is accelerating downwards. And the tension is going to be equal to the mass of the bag multiplied by gravity minus the acceleration. So it's going to be 20 multiplied by 9.81 minus 3.9. Of course, I've rounded up at some stage, but this should equal 117 because physics works. 9.81 minus 3.9, and that equals 118. And the reason why it's 118 and not 117
is because I've rounded up here and I've rounded down here, and but it's the same. Okay, they're exactly the same, so that equals that. Okay, and finally, question 41. We're nearly there. We're nearly there. Question 41. I need all of this space. Question 41 says, just a second, sorry. Question 41 states that it's a seesaw. Okay, so it's about torque. And this is what you need to know. I'm going to get rid of this too because it's annoying me and I'm a bit OCD. So we've got a couple of kids balanced on one side while their puppy is balanced on the other side. So the first child has a weight of 250 newtons and here we go. So it's 1.5 meters away from the pivot, and that's the first child over here. I'm not even gonna bother drawing like this elaborate drawing. I'm just gonna draw something very simple. Okay, the first child is 250 newtons. Okay, and they're 1.5 meters away. The next child is 200 newtons, and they are 2 meters away. So 2 meters away, and they are 200 newtons. And we're trying to find out where the puppy, the dad, is supposed to be on the other side. So the father is somewhere, well, I can tell you right now, he's going to be about there. So maybe about a meter away, depending on how much he weighs. He weighs 800 newtons, so I think he's even closer. I think he's about 70 centimeters away. Just to guess, like, let's see. We have to work it out. How far from the pivot does the father need to sit? Well, the way we do this is by making sure that everything on the left-hand side is equal to everything on the right-hand side. So the total torque on this side, the total torque on the left-hand side is equal to the total torque on the right-hand side. So let's calculate the total torque on the left-hand side. And that equals, so it's going to be torque is equal to force times radius or distance away from the pivot. So total torque, so it's going to be, we've got two of them. So it's going to be 250 times 1.5 plus, let's work it out first, 250 times 1.5, which is 375 newtons, plus the other one is 200 times 2, which is 400 newtons. So we got to add these two together, and that gives me 775 newtons, yeah? So that is the total torque on the left-hand side. What about the right-hand side? The right-hand side is going to equal the same. So we've got 775 is equivalent to 800 multiplied by R. So it's not 70, it's about 90 centimeters. So 775 divided by 800, and that equals 97 centimeters. So that person is going to be 0.97 meters away from the pivot. So the father, big lad, is going to be nearly a meter away from the pivot. So that's how you answer the first part. You work out the left-hand side, then you work out the right-hand side. And then finally, part 2 says, what is the total upward force exerted by the pivot on the seesaw? The total upward force is going to equal all their weights. So it's going to be 200 plus 250 plus 800, which equals 1,250 newtons upwards. You don't have to say upwards because the question already says exerted by the pivot on the seesaw. So it tells you the way it points. So it's fine. 1,250 newtons.
Okay, that's it for this portion. I'll see you in the next one. It'll seem seamless, but it'll be a few hours away. Or maybe I'll record it soon. I'll see you soon. Okay, in this portion of the video, we will be going through some multiple choice questions. And so this is part B. And hopefully it'll help you get some practice for some multiple choice questions. So part B, let's go. Part B. Black doesn't seem like a very good color, so let's change that. Let's see if we can. Oh, pencil? Really? Oh, that's awesome. Yeah, why not? Let's try that. Oh yeah, that's cool. Let's try that for a while. Um, but maybe we should try it with slightly darker color. Yeah, I think that'll work better. Let's see. Okay, we've got a 1,500 kilogram car experiencing a force of 1,000 newtons. What is its acceleration? So obviously force, that's cool, equals mass times acceleration. So that's going to be 500, and the force is going to be 1,000. So the acceleration is going to be 1,000 divided by 500, or 2 newtons, 2 meters per second squared. Which surface pairing has the lowest coefficient of friction? Lowest coefficient of friction means it slides easily. Highest coefficient of friction means it's very rough and there's a lot of friction there. So lowest coefficient of friction, I'm going to go ice on steel. Okay, that is obviously going to be very little friction. If a runner covers 800 meters in 200 seconds, what is their speed? Speed. You don't have to write workout in multiple choice questions, obviously. However, I think it does help, like even for you when you're doing revision or whatever. So speed equals distance over time, which equals 800 divided by 200. You don't have to do this. I'm just doing this so you understand where the question, where the answer comes from. 4 meters per second. It's a good idea, especially this is, you can do this in physics and maths as well. And in fact, many subjects, I would cover the answers. I don't even look at the answers. I try to not look at the answers. I work out the problem first, my way, and then I look at the answers. Okay, so that might be something useful to you too. Okay, so try and see if that's useful. A block weighing 15 newtons. Let's go down a bit. Oops. I'm trying to go down, but why isn't it going down? Hang on. Is it me? Oh, no, it's not me. Okay. A block weighing 15 newtons is on the surface with a coefficient of friction of 0.4. What is the frictional force? So the frictional force is going to equal mu, which is the coefficient of friction, multiplied by the normal force. So they've given me the normal force because they've given me the weight, which is equivalent to the normal force, and they've given me mu, so that's going to be times 15, and that's going to be 6 newtons. A car covers 480 kilometers in 8 hours. What is the average speed? Okay, so v av is equal to distance over time, and that equals 480 kilometers divided by 8 hours, which gives me 60 kilometers per hour. Okay, so that's that one. A ball is thrown, oops, question 6. A ball is thrown vertically upwards. What is the initial velocity? With an initial velocity of 15, what is the velocity at the highest point? So obviously this is like parabolic motion. And remember, if the initial velocity is 15 meters per second, the final velocity is going to be negative 15 meters per second. But the top velocity right here is going to be 0. Because remember, at one point it will stop before it goes back down. So it'll go up, it'll stop, and then it'll come back down. So velocity is going to be 0. However, acceleration is going to be 9.81. So the acceleration on top is going to be 9.81 down. Acceleration over here is going to be 9.81 down. Acceleration over here is going to be 9.81 down, or negative 9.81 if you prefer. The acceleration doesn't change. The acceleration relies on gravitational pull from the Earth, from the magnet of the Earth, which we call gravitational field. The velocity, however, changes. So here it's 15 meters per second. Here it's going to be about 7 meters per second. Here it's going to be about 3 meters per second. And here it's going to be 0. While here it's going to be negative 3 meters per second. Here it's going to, I think you get the picture, don't you? And so on and so forth. So the velocity on top is going to be 0. That's all you need to know. Okay. A ball is thrown, we already said that. It's going to be 0. Number 7, a bird flaps its wings downwards, exerting 50 newtons of force on the air. What is the air's reaction force? It's going to be 50 newtons upwards. 50 newtons down, 50 newtons up. Equal and opposite reaction. Third law. A car accelerates at 2 meters per second for 5 seconds from initial velocity of 3. What is the final velocity? So the final velocity is going to be Vf equals Vi plus At. So that's going to be 3 plus 5 times 2, which is going to be 13 meters per second. Let's go. Number 9, a swimmer pushes against the water with a force of 8 newtons. According to Newton's third law, what is the reaction force? It's going to be 80 newtons on the swimmer by the water. Because he's putting 80 newtons against the water, and the water is going to be pushing back with 80 newtons. If I want to jump, I push down on the floor and I jump up in the air because I put down like a force down on the floor, and that force is going to be pushing up against me. Okay, let's keep going. A box. Just going to take these off. Wow. A 30 kilogram box rests on a flat table. What is the normal force acting on it? 30 kJ. So the weight is equal to the normal force, which is equal to mg. So that's just going to be 30 times 9.81, which is going to be 294. So it's going to be 30 times 9.81, which is 294. Okay. A spring stretches 0.2 meters under a force of 10 newtons. What is its spring constant? So the spring constant, or Fs, is equal to K multiplied by delta L. So I want K, so that's going to be Fs over delta L, which is going to equal 10 newtons divided by 0.2 meters, which is going to be 50 newtons. Okay, let's keep going. Which graph features feature indicates constant speed in distant time graphs? Constant speed. So distance time graphs, I'm just going to draw some of them, some of those features. If I have something like that on a distance time graph, it means it has stopped at that position, right? A straight flat line, or a horizontal flat line, I should say. Okay, what if I have something like that? What if I have something like that? What if I have something like that? A curved line. So a straight line like this indicates there is a velocity, but it's in the opposite direction, and I can tell that it's non-changing, it's constant, it's uniform. Now, how can I tell that? Well, because the gradient doesn't change. The gradient over here equals the gradient over here, and likewise over here. So this is positive. This, on the other hand, is increasing because the gradient, the slope, is increasing, which is the tangent. So since it's increasing, there is acceleration here. There's no acceleration here. So what is it asking for? Constant speed is going to be a straight line, an upward straight line. Okay, that's the only one that makes sense. Okay, let's keep going. A 1,000 kilogram car accelerates at 4 meters per second squared. What is the net force acting on it? So F net is going to be equal to mass times acceleration, which is going to equal 1000 times 4, which is 4000 newtons. A ball is thrown straight up with an initial velocity of 20. What is the velocity at its highest point? So once again, it's 0. I think that's repeated. As we said, at the highest point, it's always 0. A 600 kilogram boat accelerates at 3.5 meters per second squared. What is the net force acting on it? So it's going to be 600 times 3.5 because F equals ma. So that is going to equal 2100. Yeah. If a car travels 150 meters in 10 seconds, what is the speed? Well, the speed is going to be 150 divided by 10 because it's distance over time, so it's going to be 15 meters per second. Two people push a 25 kilogram box. One exerts 40 newtons to the right, the other person exerts 10 newtons to the left. Calculate the net force. So here we have a situation where there's a box, 25 kilogram box. It doesn't matter what it is, since they're not asking for acceleration or anything. So there's 40 newtons being pushed in this direction, and there is 10 newtons in this direction. So what is the overall force? It's going to be 30 newtons in one direction. To the right. A cyclist accelerates 1.5 meters per second for 8 seconds, starting from rest. So that's going to be 1.5 times 8 plus 0, so 12 meters per second. Okay. Vf equals 0 plus at, which is vi, but it's 0. So 0 plus at, which is 1.5 times 8, and that just equals 12 meters per second. A motorcycle accelerates from 5 meters per second to 30 meters per second in 10 seconds. What is the acceleration? So hopefully this is pretty easy by now. So acceleration equals change in velocity over time, which is equal to 30 minus 5 all over 10, which is 2.5. 2.5 meters per second squared. 2.5 meters per second squared. A. On a velocity time graph, so this time is velocity time, and not distance time or position time. Which feature represents constant deceleration? Constant deceleration. Okay, so since it says constant and not changing, changing in this case would be, because remember the acceleration, the gradient or the slope on a velocity time graph represents the acceleration. So this represents constant acceleration, positive acceleration, all right? Because as you can see, the gradient, the slope doesn't change. The rise over the run over here is equal to the rise over the run over here, which means the acceleration over here is equal to the acceleration over here. Now, what if I change that and I go like that? Well, now we can see that the acceleration changes because the rise over run here is not equivalent to the rise over run here. Okay, now what are they asking for? They want something that shows constant deceleration. It's going to be that. It's going to be a downward straight line, because you can see it is changing velocity, but it's changing at a constant rate because the gradient is exactly the same. Okay, let's keep going. A 300, oh no, too fast. A 300 kilogram motorcycle accelerates at 2.5 meters per second. What is the net force acting on it? Times 2.5. 750 newtons. That's it. A block weighing, I think I need these again. A block weighing 25 newtons is on a surface with a coefficient of friction of 0.2. What is the frictional force acting on it? Frictional force is going to equal mu multiplied by the normal force, which is going to be 0.2 multiplied by 25, which is going to be 5 newtons. Next, which material pairing has the highest coefficient of friction? The answer is basically which one is the roughest, which one has less slide, and the answer is rubber on dry asphalt. Dry asphalt is always going to have more friction than wet asphalt. Asphalt is the same, the material they put on the roads. So the road, the top of the road, you know, with the stones and rocks and everything and stuck down on the road. So that's asphalt. Um, when it's wet, it's very slippery. So when it's dry, it's very frictiony. There's a lot of friction there. So that's the highest coefficient of friction. Let's keep going. A train travels 300 kilometers in 3 hours. What is the average speed? 300 kilometers in 3 hours. So in 1 hour, it's going to be 100 kilometers per hour. Distance over time. A block experiences a force of 20 newtons to the right and 8 newtons to the left. What is the net force acting on it? It's going to be 12 newtons to the right. Okay, because that's 20 to the right and 8 to the left. A car accelerates from rest to 25 meters per second in 5 seconds. What is the acceleration? So acceleration is equal to delta v over t, which is 25 minus 5 all over 5. So 4 meters per second squared. No, sorry. It's 25 minus 0 over 5, which is 5 meters per second squared. Careful. Don't make the same mistakes. A force of 15 newtons stretches a spring by 0.3. Calculate the spring constant. So spring constant is equal to K multiplied by delta L. And I've got, so K is equal to Fs over delta L, which equals 15 divided by 0.3, which equals 50 newtons per meter. That's that one. On a distance time graph, which feature indicates increasing speed? Increasing speed means acceleration. Distance time. So if it was a straight line like this, then I could see that the distance increases with time. So there is a velocity, but it's constant because the velocity is shown by the slope. So the slope here is the same as the slope here, and it's constant. It doesn't change. So therefore the velocity is the same. But if I want the velocity to change, I want it to be curved. A curved line shows this here is not the same as this here. Oh my god, it gets darker the more you do it. That's pretty awesome. So obviously now there's acceleration, there's a change in velocity. So it's a curved line is what we're looking for. Okay, a spring stretches 0.2 meters under a force of 10. What is the spring constant? So it's exactly the same as the one before. So 10 divided by 0.2, which equals 50 newtons per meter. Okay, and train travels 400 kilometers in 4 hours. What is the average speed? It's going to be, once again, 100 kilometers per hour. And that's that. Great. Fantastic. We did it.